All right. Welcome for the last day. We're almost done. So our class people is going from Chicago, and we talk about non-controllers.
First of all, I'd like to thank the organizers for inviting me. And welcome to the AMO session. I'm glad most of you that time folks decided to sit down for this. Yeah, so today I'll be telling you about work that I mostly did at Todadri and a little bit of a preview with what my yes. Can people hear me better? Okay. Yeah, today I'll be telling you a little bit about local probes of correlated matter in atomic and molecular quantum simulators. So because this is kind of a different experimental platform, let me start off by giving an overview, a very generic and general overview of how we try to study quantum many-body physics with the platform of ultracold gases. Of course, the question we all in this audience would like to address is how to understand strongly correlated matter, for instance, high TC, superconductivity, heavy fermion materials, et cetera, states of matter where the interactions are so strong that they cannot be added perturbatively or sometimes are not amenable to classical numerical simulations. And heavily inspired by our colleagues who work with solid state materials, we like to look at ultracold atoms, often trapped in optical lattices, as an enlarged model of condensed matter physics. So scales are far greater, order micron instead of nanometer, and the light matter interaction is understood from first principles, so we can often form very well-defined lattice potentials where we understand everything from first principles. Because our atoms and molecules are much more massive than electrons, of course, the dynamics of the particles are often much slower on milliseconds rather than pico or attoseconds. And crucially, we don't have the Coulomb interaction or the screen Coulomb interaction, but what we do have are van der Waals type interactions where the strength can often be tunable with external magnetic fields. And so in many ways, I consider this field as a way to slow down and blow up materials and simulate them in the lab. And in the last point that I brought up on that slide was the large interparticle spacing makes imaging and manipulation of individual atoms possible in a way that's quite tricky to do in the solid state. So quantum gas microscopes were first realized about 15 years ago in the group of Marcus Schreiner and Emmanuel Bloch. And here I'm showing you a picture of atoms, snapshot images concatenated one by one in our quantum gas microscope. Here, there were lithium atoms confined in a square optical lattice, and every single green point you see is a fluorescence from a single atomic emitter. And basically, how can we use these technologies, atoms in optical lattices, or a newer, also very popular platform is optical tweezer arrays, help us understand the physics of strongly correlated materials? So the first part of my talk will be on Fermi-Hubbard physics with an atomic simulator. So this was done in a group of Wasim Bakr at Princeton, carried out by myself, grad students Max and Ben. And we also acknowledge our theory collaborators, Yvonne and Eugene. And I'd also like to point out that there was also very nice work done in the group of Marcus Schreiner on very related physics. So the Fermi-Hubbard model, for this audience, I probably don't have to explain too much how such a simple model can, from which can arise very rich physics. You only have two ingredients. You have spin 1/2 fermions, two-level system for us. And these fermions can tunnel from site to site, or they can, if they're opposite spin, sit on the same lattice site and experience a Hubbard attraction or repulsion U. And from these two ingredients, at least in the square lattice, this is thought to be in many ways a minimal model of the high TC cuprate superconductors. And in quantum simulators, the square Fermi-Hubbard model has been studied for many years with a lot of really exciting results. However, today we're going to focus on another lattice geometry, a triangular lattice, which is non-bipartite. And I'm going to argue that on other lattice geometries, different types of magnetic ordering with fundamentally different microscopic origin than superexchange can be observed. So as a bit of a pedagogical background, how do we do this? With a fermionic composite atom, such as lithium-6 or potassium-40, one can isolate an internal two-level system, two hyperfine levels in the ground S state, and form an effective spin 1/2 system. And the tunneling of each particle from site to site to site is tuned by parameters such as the optical lattice spacing and the lattice depth, which we can control via intensity of our laser fields. And the on-site Hubbard interaction, U can be tuned from 0 to strongly repulsive or strongly attractive, all up until the Hubbard bandwidth by this phenomenon known as a magnetic Feshbach resonance. So that's a very nice tuning knob that we have. So recently at Princeton, we implemented a programmable optical lattice. So what you may have been more familiar with is the concept, you interfere a laser beam back on itself, it forms a sine wave. You do this in 2 dimensions, you may naturally create a square wave. However, if you add yet another laser beam and you can tune the phase of these 2 lasers with high precision, one can tune away from the square to form brick wall geometries, stripes, or crucially, what we are doing is an isotropic triangular Hubbard simulator. Now, you might look at subfigure D and say, that's not isotropic. However, yes, it's true, in the lab physical space, this does not look like an isotropic triangle. However, we can tune with lattice parameters T prime to equal Tx and Ty. So tunneling is isotropic. This was heavily inspired by a similar setup done in Emmanuel Bloch's group. So here are some of our snapshot results from our quantum gas microscope. First, let me explain the platform a little more, and then I'll talk about the science. So we make our lattice out of a series of laser beams and create this isotropic triangular Hubbard simulator. And what we take are snapshot images at the very end of any particular experimental sequence. So the red and the blue images are analog, honest-to-God camera images that we take of spin ups and spin downs. In a single shot, we get full spin charge resolution in our readout so that we can digitize those analog images. And here is that blown up. Every site we can assign with high fidelity, whether that had a single up, a single down, a doubly occupied, or a hole. So the 4 possibilities in a Hubbard system. So to tell you a little bit about the physics of magnetism that appears in the triangular Fermi-Hubbard model, let me remind you of a story that you probably all know. Let's take a Mott insulator. So in the Hubbard language, we go to repulsive on-site interactions. At half filling, the system is well known to be a Mott insulating state where even though band theory predicts it's a metal, the strong on-site repulsion really suppresses double occupancies and hole occupancies. So at low temperature, what is the magnetic ordering in a Mott insulator? Of course, it's well known that superexchange is the mechanism that really prefers antiferromagnetic correlations. If 2 spins are opposite, there's a second order process where you tunnel and tunnel back and lower the overall kinetic energy of the many-body system. However, 2 spin polarized neighbors cannot tunnel together and tunnel back because of Pauli exclusion. And therefore, for instance, this argument is very neat. On a square lattice, the ground state of the Mott insulator has this quantum checkerboard ordering. It's a Néel ordered state. Of course, superexchange also exists on the triangle. However, there you have the phenomenon of spin frustration, where if you put opposite spins on 2 corners of a plaquette, the third one becomes a little bit confused. So the antiferromagnetic ordering still persists, but in a kind of qualitatively weaker way. And it's well known that the ground state is this 120-degree spiral order. Triangular Hubbard simulators had started to pop online in around 2022, 2023, leveraging the technology of these cold atom microscopes. So two groups, the group of Peter Schaus, then at University of Virginia, and Marcus Greiner at Harvard, were able to take snapshot images of these Mott insulators. And by studying local correlation functions, like what I write on the top right, basically, we image and project all the spins into the Z basis, and then we can measure ZZ correlations as a function of how far apart these spins are. And what they measured are antiferromagnetic correlations. On the left, the blue color indicates a negative correlation. Same for subfigure B. And at Princeton, we were also able to replicate this. Here we plot a color map where the different sites indicate the different distances between the spin on site R and the spin on site R plus A. And you can see that in the 6 nearest neighbors around it, we see strong antiferromagnetic correlations consistent with a Mott insulator at our given temperature. However, we're not just interested in the half-filled system. Of course, condensed matter teaches us that it's often the doped systems that demonstrate the really unique phenomena. For instance, in the cuprates, it's the doped cuprates away from half-filling that demonstrate the D-wave superconductivity. And we were also recently inspired by work done in twisted bilayer graphene or transition metal dichalcogenides, which can also start to really be Fermi-Hubbard simulators in many instances, which is kind of neat. So let's kind of pedagogically understand the effects of doping, but let's back away from the Fermi-Hubbard model and just go to a simpler model of tunneling, a spin polarized or spinless fermion on a single spin on an empty lattice. And we'll see how if you flip the situation around, get a single hole on a spin polarized background, these are fundamentally different on a triangular lattice in a way that is distinct from a bipartite or a square lattice. So a single particle in a triangular lattice with tunneling defined as positive minimizes its energy by occupying symmetric orbitals on each bond. And you can see this, the single particle band structure E of K experiences a minimum energy of -6 tunnelings. Right. However, in a hole in a spin polarized background is fundamentally different. There's no particle hole symmetry in this system. So if I naively write the hole creation operator as a particle annihilation operator, because of the fermionic anti-commutation relationships, my Hamiltonian picks up a relative minus sign to the first situation. And the hole would actually prefer to have antisymmetric bonds across all sites, but of course in a triangle is unable to fulfill them simultaneously. This is kinetic frustration in very deep analogy to the spin frustration that I showed a few sites ago. One can also yeah.
So when you say hole, do you assume that all the other electrons form an antiferromagnet? Or?
This is a hole in a spin polarized background. So spinless fermions, right?
Yeah, sorry.
Yeah, this is just a toy conceptual model, right? And one can see this in the band structure. If I just flipped over the band structure from the last slide, now the hole is kinetically frustrated, and you can see this because its minimum energy is now at -3 tunnelings instead of -60. So the hole cannot lower its energy as much as the particle can. But nature provides a way maybe to fix this kinetic frustration when you go into a spin 1/2 system, the full Hubbard system. And let's again look at this on a single plaquette. So now, if you have a hole next to a spin triplet on both sites, if you tunnel once around this plaquette, your wave function will stay the same. However, if your hole is next to a spin flip, sorry, maybe the colors are not so distinct here, but it's supposed to be dark red and green on the bottom, and you tunnel once around this plaquette, your wave function actually picks up a global minus sign at the end. So in this way, some people call this the spin-Barry phase. It actually heals the opposite sign in the Hubbard model. And put it another way, the hole likes to preferentially be close to or bind close to a singlet bond to release its kinetic frustration and lower its kinetic energy by an amount on the order of the tunneling. It does not prefer to be next to a spin triplet. So because the hole likes to bind next to a spin flip, this is often termed a magnetic polaron or spin polaron. And the unique feature is that this quasi-particle lives at quite high temperatures, temperatures on order T, which is much hotter energy scale than super exchange, which is T squared over U. And here I list a non-exhaustive list of theory papers that have predicted the existence of this polaron. So this polaron has also a deep connection to a strange type of antiferromagnetic ordering, sometimes called Harder-Shastry antiferromagnetism. Basically, the thesis of this paper from 20 years ago looked at the infinite U, so no super exchange limit. And even then, if you put in a single hole, you mediate an effective exchange coupling between spins in a Mott insulator, and you should give rise to a distinct type of antiferromagnetism, kinetic antiferromagnetism. And this has started to be studied in both the solid state as well as in optical lattice atomic simulators. And let me just show you some experimental snapshots of our work with lithium atoms. So how can we detect the polaron with snapshot images? Well, because we have access to, in principle, all correlation functions that can be constructed out of spin or charge degrees of freedom, we can look at a three-point correlator. So on distinct lattice sites I, J, and K, if we consider that we find a hole dopant on site K, what do the nearby spins, SZ on site I, SZ on site J, how are they ordered? So this picture here is not a cartoon, it's actual data with a color map on the bottom. If we have a hole in the center, the next nearest neighbor bonds on all of the adjacent plaquettes are more likely to be antiferromagnetic, more likely to be negative compared to a background with no hole. And this actually flip sign goes to red for the next layer around. And very converse situation, the double occupancy, we can look at dopants on the charge side instead of the hole side. This likes to aggregate extra ferromagnetic ordering around it compared to the background. I'm running short on time. So maybe what I'll say is we have detected the long theorized magnetic polarons in this triangular Fermi-Hubbard simulator. And we think this is a rich platform to study the interplay between dopants, kinetic motion, and maybe even potential pairing mechanisms in materials. And I think a long sought after goal in both quantum simulators and solid state materials are whether these spin liquid phases can arise in systems with a lot of frustration. And a triangular Hubbard simulator may be a platform with which to tune towards the spin liquid phase.
So what's the difficulty in tuning to intermediate U over T? I thought that was easy for you.
Yes, this is easy to tune to intermediate U over T. Of course, the question is, how do you actually enter the chiral spin liquid phase and actually have a detection of this that people believe? So I was just talking with Ruben yesterday. There's no local correlators, of course, that we can measure that will prove a spin liquid phase, right?
That phase breaks time reversal spontaneously. So it'll be a three-spin responder.
Yes, this chiral correlator S1 dot S2 cross S3. This is quite difficult to be studied in this is quite difficult probe for us, but maybe we can talk offline of ideas. Right. In the remaining maybe 10 minutes of my talk, I wanted to actually switch gears and talk about how can we use AMO systems to simulate correlated materials with longer range interactions. Everything that can be done with like the neutral lithium atoms that I was mentioning up until now was pure on-site interactions, because neutral atoms, as one might imagine, really only experience interactions when they're right on top of each other. The contact interaction, the van der Waals 1/R6 interaction between neutral atoms falls off very steeply as you move them far apart. And yet this may prove a limit when simulating electronic matter, where you have obviously a screen-Coulomb interaction. And one specific motivation is that now there are many numerical studies, including by the Simons collaboration, that maybe suggest that the pure Hubbard square model has no superconductivity and that the ground state is actually some stripe phase. It's one may need next nearest neighbor terms in order to recover superconductivity in the Hubbard model. There are platforms available to us in the cold atom, cold molecule world that do experience long-range interactions, including if you have a high spin atom, which Richard will talk about, you have magnetic dipoles, which fall off as 1/R³. You can, of course, promote a ground state atom to a highly excited Rydberg state, in which case the dipole moment becomes up to kilodebye instead of a few debye. Or the platform that I'll be focusing on for the rest of my talk, you can go away from atoms into more complicated objects, polar molecules, which have a permanent body frame electric dipole moment in their ground state. And I won't focus so much on the comparisons between these platforms. Here's a kind of handy table, only to say that the huge downside, of course, for polar molecules is that it's much more difficult to work with molecules and atoms because of their internal degrees of freedom. But possible advantages might include you have strong interaction strengths at typical interparticle distances, but you also have the long lifetimes and long coherence times of ground state atoms. And this is just a summary of what we can work with in our quantum toolkit. Of course, with molecules, theoretically, anything that's possible to do with atoms is possible to do with molecules. And we rely on the strong electric dipole moment in molecules to tune interparticle interactions in a way that is out of reach for neutral atoms. And I will, of course, not go over the atomic physics, many decades of atomic physics that had to be necessary to achieve quantum state control over polar molecules. But maybe for those of you who are interested, the first BEC of polar molecules, the first degenerate Fermi gases of polar molecules were achieved only recently in the past 5 years or so. This gives you a sense of scale of how difficult it is to work with polar molecules because, of course, the first BEC of atoms were formed in 1995. So as a crash course for a non-AMO audience, I always like to put up this table and translate our energy scales into electron volts, which we don't often use. A molecule has electronic excitations, much like an atom, but it also has quantized vibration and rotation, unlike an atom. And we consider the molecule to be ultracold if its external temperature can be brought below to all of these internal energy scales. So really, we're talking fractions of a nano electron volt in terms of temperature. And the way that we create these polar molecules is a little bit distinct from cold atoms, but heavily inspired by the technology. Direct laser cooling of molecules is tricky and has been done to varying degrees of success, but only for very specific classes of molecules. The way to create temperatures where molecules can actually reach quantum degeneracy has been to sidestep the difficulty of laser cooling molecules, to actually prepare already ultra-cold atomic mixtures, so far mixtures of alkali metals, associate them into weakly bound molecules, and use a 2-photon optical transition to bring that excited state molecule into its absolute ground state in a totally coherent fashion where we retain the cold motional temperature of the initial sample. And the pioneering work on this was done by the Jilla team of Debbie Jin and Jin Yi. So again, at Princeton, I was involved in creating ultracold molecule experiment and synthesizing it with quantum gas microscopy for the first time. So here we had polar sodium rubidium molecules. We see a snapshot image on the bottom left that we can digitize into occupancy of single molecules in situ in a square lattice. Now, the crucial ingredient to turn on dipolar interactions in the lab, of course, condensed matter folk, you don't think of turning on interactions. Those are innate because of the electrons in your system, and dipolar interactions are a completely negligible perturbation for you. But for us, we actually need to turn on the dipolar interactions in the lab frame. Of course, the molecule has a body frame dipole moment, but that points in a random direction in the lab unless one breaks symmetry by applying a lab frame field. And one can do this by either a static electric field, in which case all of the molecules will point towards the direction of the field. But maybe a more sophisticated way to do this is to directly couple an opposite parity state of the molecule, so something with odd and even angular momentum. And we can do this with very handy microwave fields at order 5 gigahertz. So a picture of the molecule wave function that we can actually control is if we send in a pi-polarized microwave coupled to two specific states, we'll oscillate this dipole. This is like combining an s and a p orbital. It's exactly the same as your undergrad quantum mechanics. But if you apply a circularly polarized microwave and couple to another state, you get this kind of rotating peach in the lab frame. Now, that's one dipole. How do you have a dipole-dipole interaction? This dipolar interaction is, of course, anisotropic, so it depends on the collision angle of your molecules. You can either have them collide head-to-head, in which case they'll be repulsive, or they can be attractive if they're in plane. And of course, one can write down the time-averaged interaction of this dipole system, and this can be tuned from repulsive to attractive. You can zero it out. It all depends on the external fields you impose on your system. Yeah.
So, and what's the timescale of this, rotation relative to the other timescales of like Hawking?
Yes, this rotation happens at this microwave frequency of order 4 to 6 gigahertz. And this is much faster than the dynamics of the many-body system, which is order kilohertz to hopefully megahertz. So we consider this fast rotation as completely negligible. We look at the time average. It's a great question. So we like to use these molecules frozen in a lattice site, so no tunneling right now, but to study pure spin models, for instance, XYZ type Hamiltonians, where the J interaction term is nothing but this dipole-dipole interaction. And we do this with our particular molecule, which is sodium rubidium. We couple to two particular rotational states. I can mention that we can engineer our rotational coherence times to order 100 milliseconds, and other groups have since demonstrated second scale rotational coherence. So this is a particularly nice platform to study long-term quantum dynamics in a XY magnet, which is what we did. So in our system, the native Hamiltonian that we were able to implement is this XY model. You can think of this as a spin exchange model, right? A rotational excitation can hop from one neighbor to another, but it can also hop at longer interparticle distances with a 1/r³ tail. So we prepare all of our molecules, for instance, in a product state, spin up. We quench on this XY Hamiltonian to the plus X state and basically do a Ramsey sequence or a Hahn sequence where we let them evolve under no field and then do a final pi/2 readout pulse. And our microscope in this instance was only sensitive to detecting spin up state. So what we are tracking are on the left, a global quantity, total magnetization as a function of time, but we can also plot local spin-spin correlations, which I plot on the bottom left. And so you can see that the dipolar interaction actually first entangles nearest neighbor molecules, which we can see by having a finite spin-spin correlation at short times, 2 milliseconds. And then at later times, this entanglement propagates across the entire array. So we see entanglement between the diagonal neighbors and then so on and so forth until the entropy is maximized, magnetization settles to around 1/2, and the whole system is many-body entangled. And we can also plot the evolution of the correlation function, the spin-spin correlation, as a function of the nearest neighbor positions, next nearest neighbor, and third nearest neighbor. And as you might expect, these frequencies scale down as exactly 1/r³, which is the spacing of the lattice. So this is a quantum simulation in its infancy. I could still simulate the system exactly on my computer, on my laptop, no less. However, I think it's a really nice toolkit for future explorations of spin Hamiltonians in 2D that are not able to be simulated on my laptop, especially looking at long-term quantum dynamics, which is quite tricky. And I know that I'm out of time, and I will just say that at UChicago, I'm building an ultrapolar molecule experiment where I hope to circumvent a lot of the challenges in the polar molecule community by going to an intrinsically much more ionically bonded molecule, something beyond what the typical alkali molecule can do. This is potassium silver. Skip the experimental details, and I'll leave with this final slide where one target might be with natively fermionic polar molecules. One can hope to have a spin polarized system where if you turn on dipolar attraction, the ground state in 2D should hopefully be an exotic p-wave superfluid. Moreover, P plus IP may be preferenced because it gaps the Fermi surface. And so these are long-standing proposals. Sorry, I didn't put the references, dating from 10, 15 years ago. However, P-wave superfluids have been out of reach from the quantum gas community because the critical temperatures are much lower than what we can achieve in lab. So my kind of idea, and the idea of many people in the community, you'll hear about Richard's strategy for this in the next talk, is to rather raise the interaction energy scales in order to be competitive with the kinetic energy. And this is something that I think the polar molecule platform can do. And with that, I'm out of time. So I'd like to thank my team and also my collaborators at other universities, especially thanks to Dave DeMille's group at UChicago, now Johns Hopkins, for helping a lot on the silver apparatus, and theory collaborators, Mahal, Eugene, and David Hughes. And at Princeton, the work was done in Wasim Bakr's lab. Thank you.
Please.
Oh, yes.
Why is fully justifiable to think of these objects fully as dipoles and not like higher multiple?
That's a great question. So the dipolar energy will completely dominate over any other. You're right that like there's a full multipole expansion, right? There's no monopole because these are neutral, and the higher order terms are completely negligible in terms of comparison to the actual rate of the dipole-dipole interaction.
How well do the triangular lattice tornadoes simulate the threshold between antiferromagnetic and into disorder?
In what context do you mean disorder?
Speak up. Yeah, disorder from like what was said like the Mott insulator state, which may or may not be a Mott insulator to the metal regime.
Oh, yeah. So maybe I can quantitatively say that our U over T, we could tune from 0 to about 8 or 9. So of course, we cannot go into the really infinite U regime. We had some experimental limitations. So we were on the edge of the Mott insulating regime, where the probability that we would see single occupancy is like over 95%, but we still had quantum fluctuations that gave us, holes and double occupancies. And moreover, we can dope our system away from half filling to either create more holes or create more double occupancies. I don't know if that addresses your question.
Thank you.
Can you study dynamics on a single hole?
Yes.
Double?
Yes, we can place a single hole in a Hubbard system and watch it propagate. I say we've done this, but so have many other groups. You can see quantum walks, right? You can create a boundary and see a hole or a particle tunnel to the boundary and reflect off and have many reflection cycles before the decoherence effects kick in. So yeah, quantum dynamics, I think, is a definite possibility.
John?
I was wondering, particularly for the quantum simulation aspect, are you able to, because, people also talk about this in, gate-based quantum computers, and there, of course, there's, issues with noise and decoherence. And I was just wondering, can you put a number on, like, suppose that I want to simulate a zero temperature, fully unitary dynamics. How do these kinds of platforms compete with?
That's a great question. So yeah, most of the focus up until 5 or so years ago, really recently, has been on analog quantum simulation. This is, and for the near future, I think analog quantum simulations are still at much colder temperatures than the digital ones. I hope, eventually by my lifetime, eventually if you trotterize things and error correct, you will have a point where our laptops are not analog anymore. The digital, digital is maybe like a beautiful goal to reach towards, but still in the intermediate term where all digital simulator platforms, doesn't matter, atomic, superconducting circuit, have too much noise, and the overhead to encode a logical qubit from a physical qubit is still vast. And moreover, for fermionic problems, one pays a huge price to use, Jordan, Wigner encoding of fermions into spins. This makes me think that the fermionic analog simulators still have a long runway left. But of course, I and many others hope that one day we'll all have digital quantum computers to play with.
Just a comment. I think there's a lot of challenges that you just mentioned are true, but like you don't have to use Jordan Wigner, and people have prepared much lower energy states than this in digital platforms and the Hubbard models.
All right, I'm afraid we should move on. Peter, you're last late. Oh yeah, sure. Thanks. You too. Yes.
Yeah. That'd be nice. Let's picture the ground state correlations. Just measure.
Yeah,
You want that?
but I think there's more a question. I need to look at it. They have it.
But I'm comparing temperatures over, so.
Yeah. That's
But I don't think, they don't really think in that way, so.
yeah, that's why, like, I feel like there is a number in it. But it processes.
Yeah. I'm sure they're better for the native. I guess, no.
Like how?
All right, so our next speaker is Fletcher from MIT.
My name, can I call it phrase the microphone?
Oh,
Yeah.
sorry.
Yes, you should.
So it's,
Each states of ultra cold atoms.
okay, does this work? Yeah, that sounds good. Okay, cool, super. So, of course, I'd like to start by thanking the organizers first for putting this very nice workshop together, and also giving a couple of us AMO folks the chance to tell this electron-focused audience something about some of the physics that we try to do with atoms, and in Zoe's case, also molecules. I'm lucky enough to have a really nice title slide, one of the graphics people at MIT made this for us. This is, it's an edge state. In this case, this very cool metallic looking thing is a Bose-Einstein condensate of sodium. Yellow because sodium, the transition that we use to cool this atom is the 589 nanometers that you know from streetlights. racing, in this case, along a boundary of a system made not from something that you can touch, but instead from laser light. There's a ring of laser light propagating down through the system, and this atoms remain locked to this thing and flow in a unidirectional way along the edge. Okay, cool. I will also tell you, something in the second half of the talk about the platform that is just coming online in my group at MIT. I'm lucky enough with AMO systems, we usually have lots of nice lasers with different colors, which lets you put all kinds of colorful pictures on the slide. Okay, and so in the first part of the talk, I'll just give you a very sort of quick overview of a sort of program of research which we've had going at MIT over the last few years, which concerns the use of a rotating quantum gas. It's a quantum gas of atoms. Here's an image of this gas. It's rotating very quickly. It's held inside a trap which is spinning a few hundred times per second. And this thing is imaged using a high-resolution microscope. And so if you package a kind of room-sized experiment down to the essential elements, here is your rotating quantum gas, and here is a microscope, and then you can ignore the rest. Okay. And the idea here is to sort of emulate some of the physics that you might normally associate with electrons moving in a magnetic field. And so I'll briefly touch on a couple of early experiments because they kind of set the tone of what I'll spend more of the time on. The first concerns what we call geometric squeezing. This is quantum mechanical squeezing, so it's a redistribution of Heisenberg uncertainty between non-commuting observables, and in this case, those observables are the x and the y coordinates of particles in a rotating frame of reference. I'll then briefly flash some slides actually, it ended up being a surprise in the experiment. It was, we prepared a very rapidly rotating gas. We expected nothing interesting to happen. And it's one of those beautiful moments where an experiment teaches you something. It's not always as common as you'd like that to be, where we saw something unfolding on the screen in our lab, and we had absolutely no idea what was going on. And what we saw is that if we prepare a particular quantum state, this is a translationally invariant strip of atoms. It's a very strange object. It's actually every atom in this case lives in a single eigenstate under the Landau gauge. Okay, it's a very strange object. And if we turns out that if we just waited under the interplay of the gauge field the particles experience and the interactions between them, we observe the spontaneous fragmentation into droplets. Okay. The majority of my time, though, I'll spend on this much more recent experiment, which concerns a realization of chiral propagation at the boundary of a system. Here you see atoms crawling along a boundary made from laser light. I will say in front of a condensed matter audience, this is embarrassingly simple physics. It's completely single particle physics. Okay, but these edge states have been remarkably hard to realize in AMO platforms. There are currently only 2 experiments where these things have been realized in real space with a bulk and a boundary, both of which came out at the end of 2024. Okay, so they are hard for us to realize. They're much more difficult for us than in electronic systems, and so this is very nice to see this under your microscope. Okay, and so maybe the big umbrella of this physics I'll be talking about is essentially a quest to realize and to play with what we call artificial magnetic fields. And the reason that the word artificial here is important is that we do not have charged particles. You cannot just switch on a magnetic field and expect to see quantum Hall type physics unfolding. We work with neutral atoms. And so what do? Well, you need to persuade these atoms to behave as if they were charged particles moving in a magnetic field. And so, if you are a charged particle and a magnetic field is switched on and you realize that the rule book you should play by is quantum mechanics, the way that manifests is that if you perform an excursion in your environment and you come back to your starting place, you pick up a phase proportional to the loop that you've traveled through. It's the Aronoff-Bohm phase. So it essentially goes like the flux enclosed by a loop around which you travel. And that is your signature for a particle that you are a charged particle and you live in a magnetic field. And so the idea is to imprint some analog of the Aronoff-Bohm phase, imprint a geometric phase upon the atoms. And there are various wonderful ways that people have cooked up. Can't possibly digest what's on this slide. This is just a failed attempt to give enough credit. There are other experiments that I just don't have space to include. But there are many recipes people have cooked up to try and do this. But all of them are essentially trying to imprint this phase upon the atoms. Okay. Now, the approach that we take is in a way, conceptually, maybe the simplest one, and it's to work in a rotating frame of reference. And you can see at various levels, this will do the trick, both rotation and application of a B-field break time reversal symmetry. That's very hand-wavy. It maybe doesn't show that these are equivalent. Thinking more classically, you realize that the Coriolis force and the Lorentz force both take the same form. They both look like velocity crossed with something. So here we have Q V cross B and 2m, find the awkward factor of 2, mv cross omega, okay? And then more quantum mechanically, as I'll show more in a moment, the analog of the Aronoff-Bohm phase for a charged particle in a B field is provided by the so-called Sagnac phase for a massive particle under rotation. Okay. And so I always take the excuse in these types of talks to start off as long ago as possible. It gives me the chance to put up a picture, from nearly 2 centuries ago. I have no idea if the picture is from 2 centuries ago, but the event was. And so this is throwing our minds back to about 170 years to the Pantheon in Paris, which is the first public demonstration of the Foucault pendulum. I think Foucault first tested it in his basement. Okay, I guess then you check that it actually works before you make this big spectacle in the middle of Paris. Okay. And so a Foucault pendulum, it's nothing more than a 2D harmonic oscillator viewed in a frame of reference which is rotating. And we know that rotation couples to angular momentum, meaning the normal modes of the system are just a co-rotating and a counter-rotating circular swing of your pendulum. Of course, in an inertial frame, both those motions take place at omega, the natural frequency of the pendulum. In a rotating frame, their frequencies are split by the rotation rate of the reference frame. And so it's very straightforward to construct the motion. You just have to add together these 2 normal modes of the system. What you get are epicycles. And in the limit of a slow frame rotation, the pendulum appears to swing back and forth along an axis which precesses. And if you're Foucault watching, you're pretty happy. Okay, this will let me introduce some coordinates. These are very familiar, I'm sure, to many, many people, but at least let me define them before moving on. These fast counter-rotating orbits are the cyclotron orbits with coordinates psi and eta, and these orbits occur around the guiding center, which will give coordinates capital X and Y. I think these are fairly conventional coordinates for both communities. Okay, now let's imagine that we have some magical handle in the Pantheon, and we can turn up the rotation rate of the Earth, okay, to make these effects a bit more pronounced. So we can now do the same epicycle construction for an Earth which is spinning now at 80% of the pendulum's natural frequency. And if we do this, then things start to look a lot more strange. It's the same construction, but now the pendulum swings in a much more unfamiliar manner. And of course, we can go even further. So now the Earth is rotating at the natural frequency of the pendulum. And what happens in this case is that the bob still has no problem performing these fast cyclotron orbits, but now the centrifugal force upon the bob is perfectly balancing the gravitational restoring force. And so where you place this guiding center within 2D space becomes degenerate. And so without doing any calculation, which is always a nice thing to aim for, you realize that if you quantize this, you will get discrete energy levels corresponding to the different states of the cyclotron oscillator, each with a huge degeneracy corresponding to where you place the guiding center. This is a very, very familiar spectrum. This is nothing more than the lambda levels normally familiar from charged particle in a B field, here for a massive particle under rotation and without any calculation. Okay. And so the punchline of all of this is that you end up with 2 pairs of conjugate variables in your system. You have your cyclotron coordinates, which form a non-commuting pair, and your guiding center coordinates, which form a non-commuting pair. And this is important because now if you're thinking about physics somehow on big length scales and slow time scales compared to the cyclotron length and time scale, then your motion of your particle occurs within a space which is non-commutative. Okay. And we immediately see that this gives us what we need. Okay, so if X and Y, the guiding center coordinates, form a non-commuting pair, a conjugate pair, then the generator of X translations is Y and the generator of Y translations is X. And so if I take a particle, move it in a closed loop in my rotating frame and ask how its quantum state evolves, I just have to stack together 4 different translation operators. Unlike in an inertial frame, they do not all commute with each other. And a couple of lines of operator algebra shows you that you come back with a phase proportional to the area of your loop. And so in the context of a charged particle in a B field, this is the Aronoff-Bohm phase. In the context of a massive particle in a rotating frame, it's the Sagnac phase. In both cases, this geometric phase arises because your space is non-commutative. Okay. You also see your old friend, the Hall response, very straightforwardly. If you apply a force in the X direction, that's just a potential varying linearly with X, and time evolution under this potential is just a Y translator. Okay. Of course, you can generalize this to any scalar potential you like, and you realize that if you now apply a generic scalar potential V, your particles will always flow orthogonal to the local applied force. This is just the E cross B drift of electromagnetism. a kind of nice thing that you see immediately from this expression for the drift velocity is that it's generically incompressible. And this is sort of a real space instance of Liouville's theorem, because now your distribution of particles in real space is actually a phase-space distribution in the space of guiding centers. Okay, so no matter what scalar potentials you apply to this thing, you can stretch it, you can squeeze it, but you can't compress it. Okay. And so I'll just show one slide on this as sort of a first demonstration. So even though if it's a demonstration, it was just a kind of fun thing to do in the lab, which is sometimes a good reason in its own right. We performed a squeezing transformation. And as I said before, squeezing means a redistribution of Heisenberg uncertainty between non-commuting observables, where these are now the x and the y. So what this looked like in practice is that we started with, and theorists, brace yourself. We call this a symmetric gauge condensate. Usually at that point, people get very unhappy because you're somehow assigning a physical meaning to a gauge choice. What I mean by that is that we have a Bose-Einstein condensate. This is about 100,000 sodium atoms. The many-body wave function is a macroscopic occupation of one single particle wave function, and that single particle wave function is an eigenstate within the symmetric gauge. Okay, so there's a lot of words in the sentence, but what this boils down to is here are 100,000 atoms all in one eigenstate under the symmetric gauge. Okay, what we were able to do was perform a coherent transformation of this condensate into what we call a Landau gauge condensate. So here you have the same 100,000 atoms, but now you have macroscopic occupation of a single eigenstate under the Landau gauge. And so this was really fun to realize for I guess there's very few other AMO people. Zoe, you're an AMO person. But this is a really weird thing to see in an AMO experiment. Okay, so it's really an honest-to-God image taken with a camera. I say translationally invariant. At some point, there is a boundary to the system. But this is, I remember sketching these things as an undergraduate, and you have to diagonalize some Hamiltonian under the Landau gauge, and you sketch these translationally invariant strips, and it feels like such a fake thing. Well, here's one in real life.
So they're indeed non-interacting at all?
So they are weakly. They're weakly interacting. So
Then you worry about Gross-Petayevsky kind of.
I will come back to that. Yeah. Gross-Petayevsky will absolutely rear its head. Yeah. So this is the thing that this is just as we prepare this thing. If you wait, more interesting stuff happens. Okay. It turns out this is unstable against any non-zero interaction string, which we didn't. In retrospect, it becomes kind of some Bogoliubov analysis tells you this, but at the time it was a surprise. Oh, wrong button. Okay, cool. Okay, I will skip this. Okay, and so what we are left with is we call a Landau gauge condensate. It's everyone living in a single eigenstate under the Landau gauge. And so this was kind of an interesting thing to prepare in that the Hamiltonian describing the system is actually very straightforward. There are only two terms. There's a kinetic energy term involving also, of course, a vector potential. And there's a term describing interactions between the particles. The interactions are contact interactions. And so this takes a very simple form. You just ask, do two particles live on top of each other? And if so, let's give an energy cost to that. Okay, and just to show that this is, we realize what I say we have. If we now explicitly make a choice of the Landau gauge for our vector potential, then your Hamiltonian takes the following form, where you have some kinetic energy piece associated with x motion, and now an effective harmonic trap located at an x position, which is set by the y momentum. This is the sort of py-x coupling. This is the smoking gun that you're living in a B field. Okay. Here are a few eigenstates of this. We have everyone living in one of these. Okay. And what was a surprise in the lab is that sometimes experiments can be as simple as not doing anything. So here our experiment is do nothing. And if you do nothing and just wait, then what we saw was the following. So this thing developed a snaking instability and eventually fragmented into this array of droplets. Kind of a cute observation, very qualitative observation at this point, is that occasionally two of these droplets were good enough as to meet each other. And so what you get now is an interference between two little droplets of condensate. In an inertial frame, what you would see would be fringes. Okay, it's a very famous experiment from the 90s where Wolfgang showed sort of direct interference between matter waves, and what you get are straight fringes when two condensates meet each other. In this case, though, you're living in a frame with a vector potential. These little droplets of condensate are irrotational objects. They're superfluid, which means that in the rotating frame, each of them must host counterflow. Okay, and that means that when these droplets meet one another, you can't see the flow profile, but if you did, it would be counterflow at the interface. One of these guys is flowing It's very hard to show this as a laser pointer, but the interface between them, they're going in opposite directions. And so the interference between them takes the form of a street of vortices rather than straight fringes. Okay. And so, of course, you want to try and understand what's going on here. Usually, if you want to understand what's going on, it's helpful to think about different limits. And so let's first think about the limit of the lowest lambda level, so that everyone is living in the lowest band of the system. And so when you do this, it's fairly straightforward. You can take your true Hamiltonian, you can project the lowest lambda level, make a Bogoliubov approximation. You basically exploit the fact that everyone is initially in a single, everyone is initially in the same single particle wave function. That lets you reduce your quartic Hamiltonian to a quadratic one, and what you're left with is a sort of generic bosonic. There are terms which basically count how many particles live in a specific state and assign some energy cost to that. The more interesting term is the second one. Okay, this arises from interactions and essentially describes pair production. It describes a process where you take two particles from the initial condensate and you scatter them into plus or minus k. Okay, and that's the only thing interactions are allowed to do at lowest order. It's this term. So in an inertial frame condensate, it gives rise to quantum depletion. In a sort of simple model of liquid helium, this is the term that gives rise to quantum depletion. But in those systems, this pair production is always weak compared to this first term. What we have in this case is a situation where pair production dominates. Okay, so the second term in the Hamiltonian becomes stronger than the first. There are sort of two reasons why that happens. One is that you're in a flat band, and so there's now no energy putting particles into different K states. The slightly maybe nicer one is that because you're in a magnetic field, when you scatter particles into different momentum states, you also change their position. There's a coupling between position and momentum. And so when you do this scattering, you also shift particles with respect to the original condensate, and there's a sort of interaction energy advantage to doing that. And so together, these conspire to give you basically a runaway process where you get an exponential growth in the populations of plus or minus k. And so the condensate, or the wave function that you end up with, ends up being a superposition of, it depends how you label these, but k equals 0. So everyone's initially in this state. And then you scatter scatter atoms into plus or minus k. You have to interfere everyone together coherently. And what you get is a snaky instability. Okay. Now, you could, of course, just diagonalize this directly. This is just a quadratic Hamiltonian. So why not just find the excitation spectrum and be done with it? And that's what's shown in the bottom right. And what you find is indeed a collective excitation spectrum, which is imaginary. This dashed line indicates that the energy becomes imaginary. So it's a dynamical instability. Now, in the opposite limit, many lambda levels are occupied. In that case, you should recover classical superfluid hydrodynamics. You shouldn't have H bars flying around. Who cares if you occupy 1,000 or 1,000,000 lambda levels? Once it's many, it's many. And so now we should think about a more hydrodynamic picture. And one way to do that is to think about the superfluid flow profile. Okay, and so what I mean by this is it's the thing you would measure if you dropped ping pong balls into your superfluid and watched how it did. Okay, so it's a physical observable. Normally, you'd associate that with this term. The superfluid flow profile looks like the gradient of the phase of the superfluid wave function. But to make things gauge invariant, you also need to include the extra vector potential piece. And this is interesting because it means that even if you are in an eigenstate of your system so that the phase is uniform, because you have a vector potential, there is a flow profile. And so what we have created here is a Landau gauge condensate, if I can use that phrase again. And that means that if you could peer inside it, what you would see is that particles actually flow up along one side of the strip and they flow down along the other. And this type of counterflow, it's very, very reminiscent of something like the Kelvin-Helmholtz instability. It turns out this instability shows up actually in several other places in nature. It's called the diocotron instability in a cyclotron. It arises from an interplay of the B field of the cyclotron and Coulomb repulsion of the particles. So this is sort of a time series of this fragmentation of a charged beam in a cyclotron. It turns out the same thing happens in the oceans. If you have what's called a line plume, which is when there's I learned this from a colleague at MIT. If you have a line plume, which imagine some volcanic ridge on the floor of the ocean, and it's emitting some strip of buoyant fluid, as that rises up through the ocean, the rotation of the Earth drives the same fragmentation. So these are sort of swirls of fluid in a tank, I think in this case, a tank of water, which is rotating. Okay, so it's pretty fun to take an instability which happens in the oceans. Here you can take it all the way to the lowest lambda level. Okay. So let me kind of skip over some details. I'm sorry for doing that, but I want to move on and extract some fun stuff from this instability. The only plot I will dwell on is this one showing this is the rate at which this fragmentation occurs on the y-axis, plotted against, so this is the ratio of the chemical potential to the cyclotron frequency. And so in very loose language, this top x-axis is the number of lambda levels mixed into the superfluid wave function. Okay, and what's very sort of cute to see is that as this number becomes large, this fragmentation rate approaches a constant. It approaches the rate you would expect from classical superfluid hydrodynamics and becomes independent of the number of lambda levels mixed in. But as it becomes of order unity, you see it with a regime where instead this fragmentation rate becomes set purely by the chemical potential. And this is sort of a smoking gun that you are entering the lowest lambda level. You're in a single flat band. The only energy scale you have is interactions. And so any dynamics that happens must be set by the interaction strength. It's the only way you can construct a timescale. Okay, and so now let me come to what I wanted to spend a little bit more time on, which is this realization of chiral propagation at a boundary. And so if you'll humor me for a moment, you know, I don't apologize for keeping things simple. Maybe there are people in the audience who are, need a little reminder. So let's just spend a slide on this. So what are we talking about here? So we know very well that if we take a magnetic field and we place electrons into it, they'll perform cyclotron orbits, okay? And if you now introduce a boundary to the system, this chirality of the cyclotron orbits is reflected in as a directionality of the skipping of particles along the edge. This picture survives, first quantization pretty well. So now we're imagining a wall which is running along the x direction. Here, green is repulsive. Okay, so the wall is translationally invariant along x. Let's write down the Hamiltonian. Well, we have a translation invariance along x. So let's make a choice of the Landau gauge to reflect that symmetry. And the Hamiltonian you end up with is essentially a harmonic trap. It looks like the particles live in a harmonic trap whose y position is locked to the momentum along the boundary, okay, plus the wall potential. And if you just stare at this Hamiltonian for a minute or two, you realize there are two very different limits. If the wave vector k is sort of large and negative, then this effective harmonic trap lives deep in the bulk of the material and the atoms never explore the edge, and you should recover your flat dispersion. But if, on the other hand, this wave vector becomes large and positive, well, now this effective harmonic trap moves off into the forbidden region of the wall. The atoms say, hey, come on, I can't go there. There's this wall stopping me. The atoms remain locked at the wall position. And so this harmonic trap just gives you an energy cost which increases quadratically with k. And if you keep track of all of your n's and 2's and h bars and so on, what you expect is an energy which looks something like h bar squared k squared over 2m, which is extremely familiar as the spectrum of a free particle. The crucial difference being that this dispersion hosts only positive velocity. Good. And so again, this has been, people are not unaware that this is cool physics to try and address. There's been a noble history of trying to realize this type of physics in cold atom platforms. The majority, there's one experiment here from Marcus's group where they have, I think, it's a ladder geometry, so maybe like 2 sites, maybe 3, I think 2 or 3 sites, but sort of a ladder type geometry. But all other experiments here made use of what's called synthetic dimensions. Synthetic dimensions means that you have one spatial dimension, and your second dimension is provided by some internal state manifold of the atoms. And that had the big advantage that it naturally provides a very clean and sharp edge. There is a sort of limit to the angular momentum that the atom can have. The disadvantage is that it's very difficult to see how to generalize those experiments to explore, for example, the structure of boundaries or the role of interactions. Okay. And so there's been a sort of long interest in trying to realize these things in real space. And that's what sort of we're reporting here. And I point out that actually the reference is super out of date. The 2 works appeared back to back in the end. I'm sorry, I need to update this. But a related work came out of the Munich group led by Monika Eidelsberger, where they realized sort of edge transport in real space, but in this case in a driven optical lattice rather than in a rotating gas system. Okay, so yeah, I guess I have a fewer minutes than I thought, so I will move a little bit quickly, but at least show some nice images. I will maybe gloss over how we get particles to the boundary. Okay, so we take our rotating system. The only difference to before is that we now apply a sharp optical ring. This is a ring of laser light propagating down through our system, which is projected using a high resolution objective, and it provides a repulsive boundary for the atoms. Okay, we then induce atoms to flow towards the edge, and we can controllably give them varying impulses, or varying, or essentially by control. We have some force which is azimuthal, and we just control how long we apply that force for, which lets us control what the momentum of these particles along the boundary is. Okay, and here's an image of these particles first striking the edge. They've started at the center. They've flown out along the diagonal of the system in both directions. When they meet the edge, they indeed begin to propagate clockwise around the boundary. Just by controlling for how long do we apply a force in the azimuthal direction, we can control what their momentum along the boundary is. We can then switch off the applied force. They subsequently propagate with fixed wave vector. And so the bottom line is that we can controllably put them at any point we like up on this edge dispersion. So here they go. This is another couple of snapshots that you see the strip of atoms which is propagating around the boundary of the system. Just a nice little aside, the thickness of this strip is actually set by the 0-point cyclotron orbits of the lowest lambda level. So it's really Heisenberg uncertainty which is limiting the thickness. It's really a little atomic wave packet, and this size is just the magnetic length. Okay, and the first thing you can do is to pull out the speed of this mode as a function of wave vector, and what you indeed find is that it's linear, okay, which is a very familiar result. It's just a free particle, but it was pretty cool to see these free particles appearing at the back of our system. Okay, here's a related experiment by some collaborators. Okay. This image is actually a response to a referee. We had a very tough time with one of our referees who said that these absolutely would not be robust and would fall apart the moment there was an obstacle. So we made an obstacle, and so here it is. So we now apply an additional, it's a tweezer beam, so it's a repulsive spot of laser light which we place at some point on the boundary, and what you see is that as this mode reaches this, it crawls around and it continues on its way. And on the right, this is a GP simulation, a Gross-Piatiewski simulation of the same experiment. Okay. Okay, so yeah, let me quickly mention this. Our sort of first attempt to exploit the fact that we're now in free space rather than synthetic space is to look at the role of edge sharpness. And so now we consider not a sharp wall, but a linear wall. So it's a wall which is linear, and it has some steepness alpha, which basically measures how many cyclotron frequencies they vary by over one magnetic length. Okay. And again, if you stare at this for a moment, you realize there are two different regimes. If the wave vector of your mode is comparable to alpha, then that means that your wave packet will explore this kink. And so at that point, as long as alpha is much larger than 1, it shouldn't really matter whether it's 10 or 100 or a million. Okay, at some point, just have hard wall behavior independent of the value of alpha. On the other hand, this is kind of a depressing thing to realize for us, which I'll explain in a moment. You can always find a sufficiently large wave vector so that your edge wave packet lives up on the linear region of your potential. And that's important because a linear potential does not mix cyclotron and guiding centers, no matter how strong it is. And therefore, you'll recover E cross B drift. And so as an experimentalist, this was kind of a punishing thing to realize because you put a tremendous amount of work into creating very clean, very sharp optical potentials. And then you realize that no matter how sharp you've made it, you can always find a wave vector that you'll recover E cross B drift. Okay. And so just to summarize that expectation, we think that if we look at the speed of the edge mode, edge sharpness, there should be an E cross B type regime where the speed is proportional to the steepness, and then this should eventually saturate at a propagation speed independent of the steepness set purely by the wave vector and the free particle dispersion. Anyway, this is what we measured. So the black line, this is theory, that's the expectation we showed on the previous slide, and the red point the data. So you indeed see you vary the steepness of this optical potential. Was not such an easy experiment to do. This crossover E cross B drift to what's essentially a quantum version of the skipping of electrons along a half. I will gloss over this. Also, spectroscopy basically infer the splitting between the ground and the first excited edge band by looking at what's actually a dipole mode. As the particles propagate along the boundary, there's also a small radial oscillation, and that frequency basically tells you it's splitting the first excited edge mode. Okay. Here are some pictures of some rotating gases now in a bucket potential. It's full of now vortex liquid. This is sort of fun. At that point, we kind of gave up. So in these images, here the chemical potential is comparable to the cyclotron frequency. It means you're sort of on the edge of lowest lambda level type physics, but the filling fraction is still pretty high. This has been an ongoing push in cold atoms to get this down, but in these experiments, we can get down to maybe tens, okay, maybe tens of particles per flux quantum. It's very, very difficult with these imaging techniques to get lower because you don't have. So for that reason, this experiment is now a quantum gas microscope. So here, every dot is a single atom. And what I'm actually showing here is the same fragmentation, the same instability that I showed earlier now result at the levels. Okay. And then I think in my last minus, I never see yet minus, it's minus of order, maybe, okay, well, that's a few minutes, yeah. Let me just show you some pictures of this experiment, which is currently coming online. My group at MIT, and it's a quantum gas mixture meaning two different elements, in this case of erbium and lithium. Okay, so here are some nice images. There are various reasons why this is an appealing mixture. To realize in the context, though, of this workshop, let me focus on one. Zoe's already done a lot of the hard work for me by motivating this, and it's to realize, or the realization of so-called topological superfluidity. It's the only time I use the word topological in this talk. I try to use that word as little as possible, but here I allow myself to do it. And I mean, what is the goal here? So essentially what you want is superfluid pairing spin polarized fermions. And I was talking to people at dinner last night about this. There are things that are hard and easy in condensed matter and hard and easy in AMO, and these are can be very orthogonal to one another. So in our case, spin polarized fermions is trivial. It's the easiest thing in the world. Okay, you really need to think about it. The hard thing for us is long-range attraction between them, because if you have spin polarized fermions, the good old contact interactions, which has been the workhorse of many body physics in AMO, are no good for you because they never see each other because of Pauli. You need long-range forces between them. That's difficult for us. Okay, so Zoe already motivated this, talked a little bit about different approaches people have taken. Zoe's big interest is using molecules, super exciting direction. In this case, we have a slightly different proposal, and it's to use phonons. It's very inspired. There's nothing creative here. We just copy what materials already give you in electronic systems, and it's to use phonons. And the idea is to immerse fermionic atoms inside a Bose-Einstein condensate of a different species. And this BEC now provides you a phononic medium. It's a medium whose low energy excitations are phonons, and phonon exchange between your particles builds you what's the Yukawa potential between your particles. So on paper, these promise to be extremely strong, and it's a direction that's been not explored so much. A little bit of work in Cheng's group at Chicago, but still a kind of unexplored direction aside from that in AMO. Okay, let me at least motivate this mixture on one slide because it lets me show some BCS theory, which I'm sure you guys will love. We know that generically within BCS theory, the pairing temperature for superconductivity or superfluidity looks something like the Fermi energy, and then an exponential if there's a -2, right? And then a density of states at the Fermi surface, and then the coupling between your fermions. And so if you now package things together, so for years people have been making S-wave superfluids using potentials. In that case, you take your density of states, the Fermi surface, and you take the coupling between the fermions provided by contact interactions. Here, A is the S-wave scattering length. What you find is a whole bunch of cancellations, and all that ends up mattering is the product of the Fermi wave vector and the scattering length. So all you can do is make KFA large, and that's it. You've done the best you can. Now, when it comes to these mediated interactions, the story is a bit different. Again, you take the density of states on the surface. Now, though, your coupling is a second-order one. You have essentially the second-order coupling arising from sort of the bare Fermi-Bose contact potentials, and you also have a propagator. It basically describes how easily do phonons propagate in your system, and together this composite object gives you the effective coupling between fermions. And now the punchline is if you package things together, what you find is a pairing temperature which goes exponentially with the mass ratio. It's a very, very strong scaling. You really want heavy fermions and you really want light bosons. And so one of the big motivations of this erbium-lithium mixture is it gives you a colossal mass ratio. It's a ratio of 24. Lithium is the lightest boson we have. Erbium is one of the heavier fermions. There's a reason for choosing that rather than something like a terbium, which I will not go into. But that is the idea, okay? And so let me finish because it's the morning and we had this great dinner last night, and so it's nice just to look at some stuff. I realized that not everyone in the room would have seen an AMO lab, so I'd at least show a few images to show you that we really build experiments. So here, these are some images of some atomic ovens. So buried in here, there's a 1300 Celsius erbium oven. here about a 500 Celsius lithium oven. Out of these ovens come atomic beams. Here's an atomic beam of erbium atoms. Here's an atomic beam of lithium. You have a whole bunch of lasers. These are cooling lasers for erbium, 2 different transitions that we work with. The red, anyone who's worked with lithium feels that some circuit fires, and they know that's 671 nanometers. So here's a lithium optical table. All of these are sent into a vacuum chamber. If you do things right, you get laser-cooled samples of both species. Here's a little cloud of lithium. Here's a little cloud of erbium. Here they are together. We then transport the atoms. You have a 200-watt laser focused to a point, which we translate through the vacuum chamber, and it brings them into a glass cell, which is addressed by high-resolution microscopes. It's like an iceberg. Here is the nose of one microscope. Here is the side of another. Here are a whole bunch of optics getting lasers into the system. One of my students made a much nicer diagram, but you have to get very creative with space and dichroic mirrors to bring all these beams onto your atoms. And if you do things right, my students actually sent me this yesterday. So we now have degenerate gases of both species living inside the system. Here blue is erbium. Here red is lithium. In this case, both are Bose-Einstein condensates living happily together. But sort of in the short term, we'll then push the erbium from the bosonic isotope to the fermion. Okay, I'm sorry for going a little bit over, but let me finish with some nice pictures and some names of the wonderful folks involved in the work. Thank you.
I will allow 1, maybe 2 if you ask nicely. Yes, Bill.
With these edge states, is there an experiment that you could do to test whether they sort of travel coherently around the edge, like, some kind of interference with the original?
Yes, they absolutely. So we did also play a little bit of time with this. You can imprint kind of creative geometries so that at some point 2 meet each other. Actually, one reason that the images stop when they do, okay, is that if you just wait a little bit more, you see exactly what you described. So as this edge meets its friends here, you see fringes. There's absolutely coherence. But at that point, you don't know then what else to say. Like, they're coherent, but there wasn't so much sort of interesting stuff to then pull out of that. So we did have some ideas for kind of whether you could build kind of atomtronic type circuits of these things. People have had great difficulty in kind of guiding atoms coherently around interesting circuits, because in an inertial frame, forces give you accelerations, right? And so noise, just the punishingness of noise gets worse and worse with time. So one idea is that it's sort of nice that in the rotating frame, forces give you not acceleration, but velocity. So these things are somehow much more robust than trying to guide atoms in an inertial frame. So we have some ideas of kind of imprinting more creative geometries. Honestly, we kind of got distracted by imaging atoms instead of these are sort of bulk absorption images, which is why we sort of pushed in this direction. But yes, this is an idea. These are ideas that we're playing with. What you could do.
All right, in my mind. Today they decided to torture you, free toast before coffee break. You will have to suffer.
I'm honored to be your torturer.
I haven't seen. Oh, wait.
My computer shows it. Yeah, my computer shows. Oh, okay. We'll switch it to the HTML. Or I can try. Okay, why don't I try this? Oh, now it's. Check. Yeah. I tried this one. There you go. You're just fine. Okay.
So we have Seth Musser from Maryland.
Yeah, okay, so let me, in the interest of seeing what my time is, I'll start my timer. Okay. So thank you to the organizers for organizing this really interesting session, or conference rather. I, as has been said, am Seth Musser. I'm at CMTC as a postdoc right now. And today I'll be telling you about ordering the topological order in the fractional quantum Hall effect. So this work appeared on the archive last night, and I have a QR code here, and there will be one at the here are my collaborators. So without further ado, I think you've heard from many people much more illustrious than myself about how exciting recent developments in van der Waals materials have been recently. In particular, the fractional quantum Hall effect at zero magnetic field has been a really stunning advance in this field. I'm putting up two images, one from the twisted TMD setup and one from the rhombohedral graphene setup. And both of these are displaying the same fractional quantum Hall type phases. Many, as we'll see later, are happening at Jane sequence fillings. And this has been confirmed by transport measurements as well as strata formula measurements. And additionally, I think there are some, Mohammed Hafizzi at Maryland was telling me about optical sensing probes they use to detect that these are incompressible phases with fractional quantum Hall response. The microscopics between these different systems are very different. So in the rhombohedral case, you need interaction to get a well-separated flat band, shown here. And in the TMD case, you do not. I think you'll hear from Senthil later today. There's a really exciting additional recent work that's been posted where superconductivity was observed near fraction. I'll note that in this experiment, you see some hints of traditional fractional quantum Hall physics. They have these phases, the reentrant integer quantum anomalous Hall phases, where the strata formula doesn't agree with transport in a way that's really reminiscent of the reentrant integer quantum Hall. So we have these systems, they have different microscopics between themselves, but some of the physics looks similar to the fractional quantum Hall you might know from continuum gallium arsenide. So I wanted to make sure at least one person in the conference had some appeal for maybe a practical application of these zero magnetic field fractional quantum Hall states. So I wanted to reference this proposal by Jason back in 2013 about proximatizing fractional quantum Hall edge states with superconductors to get Kerr fermions, which could in principle do universal topological quantum computing. So I was talking with a colleague at CMTC, and she knows the experimental literature here much better than I do. There have been attempts to do this with gallium arsenide, but there you have to have a magnetic field to get the fractional quantum Hall state. So you need a superconductor with a large critical field. And that has kind of constrained this area. So this is, I think, an interesting potential practical application. But I confess that I'm a theorist, so I'm interested in the different microscopics. The fact that these might realize new states of matter. So we see that there's already different microscopics sort of between the different realizations of fractional quantum anomalous Hall. But what about a difference with the continuum case? So in principle, of course, the presence of a lattice could lead to very different microscopics. And I want to, because this is so new, I want to point out at least one example numerically where this may have been seen. So Emil Bergholz's group was looking at a admittedly somewhat exotic scenario of double twisted bilayer graphene, but they see the stabilization of phases with Fibonacci anyons where you wouldn't expect them if you did not have an underlying. So I think this motivated us to ask kind of a basic question, which is, suppose you come to me and you're an experimentalist and you say, I've measured a phase of matter. It is incompressible and it has a fractional value of the Hall conductivity. So throughout, I'll be saying this is P over Q, P and Q are co-prime integers. And you want to know what phases of matter are consistent with this value. So it's kind of my job. I'm the computer who should tell you this. So for example, say you come to me with sigma h is 1/3. So we know from continuum fractional quantum Hall very well that the Laughlin state at 1/3 filling would be an acceptable phase of matter for this. But we could always stack additional topological theories on top of it. And as long as they're neutral, they won't change the Hall conductivity. So maybe you come to me and you're looking at gallium arsenide and you say, look, I saw sigma h is 1/3. And I tell you in some robotic monotone voice, well, U1 level 3 is okay, but also U1 level 3 stacked with a Fibonacci. And you would look at me and say, why would I ever get a Fibonacci? Like, who ordered that? And you would probably be right. In fractional quantum Hall systems, you rarely see this. However, the different microscopics here motivated us to really be more comprehensive in our answer. So actually give you the list and then let you be able to discriminate with experiments between. So the phases that you get will be topological, and this is due to the famous Laughlin flux threading argument. So let me take your fractional quantum Hall system and I'm going to put it on an annulus and pierce it with 2 pi flux. Because I'm gapped, I can adiabatically thread that. And I will go from a ground state to a ground state. And as I do, Maxwell will tell me that I have a magnetic field which is changing in time. And so that will generate a circulating electric current. But this is a Hall system. And so I'll get a transverse flow of current from the outer to the inner edge of the annulus. And by the time I'm done threading 2 pi flux, I will move a fractional charge of P over Q, or sigma h. But that can't be an electron. Obviously, the electron does not have a fractional charge. It says sigma h is 1/3. So this is suggesting that I have some fractionalization. And so many other people have built on this. But having established kind of that this is interesting and we want to find these phases and they're topological, let me give a little bit more of a mathematical picture. So our basic question is we want to know the topological orders, which we know we must have, which are consistent with this fractional sigma h. So we have our U1 symmetry that needs to be there for us to couple to the background gauge field in the first place. So we know that's there. And we've measured, let's say, a fractional sigma h. And we put these into what I'm going to affectionately call their consistency machine. And it spits out some list of topological orders. And then you can tell people how do you discriminate between them. So the reason I put this up here is because often I tell people who are familiar with traditional symmetry enriched topological order, this kind of thing. And they're familiar with running this machine in the opposite direction. So they're familiar with, I already know I have a topological order. Maybe it's U1 level 3, maybe it's Ising anion. And you give me the topological order you already know, and you say it has U1 symmetry, and you put it into the symmetry enrichment machine. Notice it's running in the opposite direction. And I tell you, here are the ways to assign charge to your theory. So maybe in the Ising anion theory, we can give the sigma particle 1/2 charge or 0 model. And with that comes a value of the Hall conductivity. But you can kind of see why this might not satisfy an experimentalist who doesn't know what topological order they have. They know the sigma h that they measure. Okay, so that's why we want to run it in the reverse direction. You'll have to forgive my use of cartoons. I really like those. So, so we're going to start with a topological order, which will have some anyons. And my collection of anyons are some, I might have abelian anyons, And I represented this as two halves of one that fuse together to make another abelian enneagon. Or I might have non-abelian enneagens, which are represented by larger circles. The colors mean nothing other than to make it look pretty. And so I have a collection of enneagens. They have some fusion rules and they have some braiding rules, and these are consistent according to the pentagon and hexagon equations. I also know I have U1 symmetry in the problem, so I'm going to have to enrich this with U1. So let's say I give this guy 1/2 charge. Hopefully from the picture it's clear why I'm saying 1/2. And I fuse two 1/2s, I should get a 1. The same will be true for non-abelian. I need my charges to respect this fusion. So that's what I mean when I say I enrich by U1. And I'll also require that I have the Hall conductivity that I've observed in a theorem. So this last requirement is called formally a spin C theory, but hopefully this is straightforward just from thinking of building your system with electrons. So in your enneagon theory, you have two objects which braid trivially with everything. It's a bosonic vacuum and a Fermi. And let's imagine that I start with a system of electrons. Any local particle is going to braid trivially with all enneagon. And I want to build a local boson from electrons. We know that you'll end up having to Cooper pair them. So any local boson is made out of even numbers of electrons and it will have even charge. Any local fermion will be made out of odd numbers of electrons and it will have odd charge. So this is the spin C theory. Okay, so we have our setting. We're looking for our topological order and we know the rules, or at least we know the references where the rules are contained. So that was the situation I found myself in. Now we can look back at, for this field, maybe not ancient history, but look at these classic seminal works from Halperin, Arovis, Schrieffer, Wilczek, many others. And we can look back at them in the framework of these enneagon theories. So earlier I was talking about a 2π flux. I want to thread this 2π flux. I return to a ground state. And this 2π flux can be identified with an enneagon, which we'll call the Ison V. So the Ison V carries this 2π flux. And now let's imagine that I put another enneagon A in here and I braid it with V. I'm taking this enneagon around a 2π flux. So I should accumulate a phase in the wave function, which is exactly 2π times the charge of that enneagon, because I'm detecting the charge with the 2π flux. But what that means is that the braiding phase of my enneagon A with V is equal to 2π times its charge. So the Ison X the charge via braiding. Okay, so that I know just from this U1 symmetry enrichment. Now I want to use the information of the Hall conductivity. Earlier I told you when I threaded this flux in, I brought in sigma H charge from the outer to the inner edge. So I can think of this Ison after 2π flux threading as itself having a charge of sigma H, because that's how much I bring in when I introduce a Ison. But then you imagine I replace my arbitrary enneagon A with V, and I know that my braiding of V with itself detects the charge of V, and that's sigma H. So this tells you that V braids non-trivially with itself, let's say for 1/3, which is familiar if you thought about the Laughlin 1/3 state. And from the facts that I told you here, it is possible to prove, although there is one step that is a little tricky, and Kapustin and others have worked on it, that the Ison is an abelian enneagon, which has topological spin given by pi times sigma H, and it has charge given by sigma H. So we know this enneagon is in our theory just because we have sigma H. And we'd like to get some constraints, get some handle on the possible theories that we get from our consistency machine. So if the Ison is in the theory is closed under fusion when I do these fusion processes. So all powers of the Bison need to be in the theory. So in particular, we can just take powers of the Bison until it starts to break trivially with everything and gets back to 1 in this algebraic theory. But this bosonic, whatever is equivalent to a local bosonic excitation, which is what 1 means in my anyon theory, should have an integer charge. And we know the Bison has charge P over Q, so I'll need at least Q copies, and it'll need to be a multiple of Q if it's more. So the order is S, and that's a product of L times Q. We call this abelian group BQL comma PL. I apologize for the mathematical notation, but if you read the paper as I hope, then hopefully this talk makes it more digestible. So the first index here just tells you how many non-trivial powers of the Bison you have, and the second tells you its topological spin. And this was described before in a paper by Nadi. By the way, if I don't mention the references, they are there, hopefully. I know this is on YouTube, so people will forgive me. Okay, so let me just go back and we'll look at some familiar examples at odd denominator to kind of orient ourselves with this perspective. So say we look at Laughlin, Jane, hierarchy states. If we have an odd denominator, all of these have exactly the number of anyons equal to the denominator. So Laughlin 1/3 has 3 anyons, 1/5, 5. Jane 2/5, 5 anyons. The wave functions themselves may look different, prepared in the same sigma h, but they describe the same anyon theory. And they all, the order of the Bison is exactly the denominator at odd q. There are 2 more exotic examples, which are the Reed-Rezai states at 2 + 2/5 and 2 + 3/5. So it turns out, this was mentioned in Parsa Vanderson's thesis, that you can understand these as being the stacking of a Fibonacci theory or its time reversal with these Bisons. So we have kind of an uncharged sector stacking on top of what's generated by the Bisons. Okay, I want now to go more general with my math. I promise it's for a reason, because when we go to even denominator, those of you who know about Moore Reed, these types of states, you know that it's more complicated at even denominator. So I'll need to build, and I have time to build some machinery. So I'm going to keep focusing on odd q, but I'll come back to even. So let's say that L is equal to 1. So that means the number of powers of the Bison that I've introduced by flux threading is exactly equal to the denominator of the Hall conjugate. So then it turns out that this collection here of the Bison and all of its powers, if you look at the braiding on this group, the braiding is non-degenerate. And there's this theorem in modular tensor categories, which says that if you have a subset of your theory, which is itself a modular tensor category, then you can break it apart. It's almost analogous to something when you think about vector spaces, where you're looking at orthogonal spaces. So these are kind of orthogonal modular tensor categories. So if the order of the Bison is exactly q, you will realize that you can split off all your charge sector, which is generated by the Bison, from your uncharged sector, which is some bosonic topological order. And we saw that in the Reed-Rezai example, because we split off the Bison from the Fibonacci sector. So that is an example of this observation. On the other hand, and now we're really beyond the scope of what's ever been seen in numerics. If the order of the Bison is not q for odd denominator, then we can get ourselves back to having order q Bison. And we can do so using a process that I learned from Fiona's great review article on anyon condensation. So we'll note that this v to the q, and I'm attaching some powers of the electron. These don't really matter for braiding, but they're important for getting the charge right. So we have this even charge self boson, which is like V to the Q. And we can condense it and take the theory back to the order of the boson being Q. And then it factorizes nicely. So we have this kind of picture, which we'll use for even Q. So this isn't math for math's sake, maybe a little bit, but we have some symmetry enriched topological orders T, and they have the right Hall conductivity as we've designed them. And maybe their order of the boson is larger than it should be. So L is greater than 1. Then we condense this V to the Q, and we descend to this theory where the charge sector splits off, and then we remove the uncharged sector. So there's like a two-step process. The reason to think about this is that we can actually reverse this. So if we start, it's almost like a genealogy. If you look at the children and you reverse and you say, what are the possible parents of the children? We know that in the odd Q sector, this is always the child. And so if we know a little more information, we can go up the family tree to try to reconstruct there. Okay, so I promised even Q, I keep alluding to it. And I want to give a concrete case in which what we do has been useful to someone, even if it's not experiment yet. So Yinghai Wu was Jane's student and is now working with his own student to study the fractional quantum Hall effect at 3/4 filling. And they were doing some ED and they found a ground state degeneracy of 12. So they have a little more data than the experimentalists have. The experimentalists know sigma H, but not necessarily how many anyons they have. In numerics, you have a little more control. So that big list of topological orders, we can narrow down further because you can tell me I've done ED, and not only do I know sigma H, filling factor, I know the number of anyons, which is the number of ground states on a torus. And so that helps us zoom in and say, what are the topological orders? It will turn out that this is the smallest possible number of anyons, which we'll come back to. I think we did not expect this when we started, but it ends up being an interesting observation. Basically, all observed fractional quantum Hall states have the smallest number of anyons given sigma H. Okay, anyway, they found this ground state degeneracy. We can prove this is the smallest it can be, and we can give them exactly the 4 topological orders that are consistent with this. Okay, so what's new with even Q? We'll go back to this V to the Q again. So if Q is even, I told you P and Q are co-prime, that means P is odd. And in particular, if I look at what the charge of V to the Q is now, it's an odd charge object, and it's a self boson. So we have this odd charge boson. And earlier I told you, and you probably thought this is very abstract, why does he keep talking about spin C? That when I have local bosons, they need to be even charged in a system made out of electrons. Again, that's because we're making them out of Cooper pairs. So we have this odd charge boson, it can't be local. So that tells us V to the Q is not like the bosonic vacuum. And that means there needs to be an enyon in the theory which braids with V to the Q. This will be familiar to you if you know the more Reed state. There's this quarter charge non-abelian enyon. I'm suggestively calling it sigma. So now let's just count we know the charge of V. So we can look at everything generated by V and things generated by V fused with sigma. We just count how many unique charges there are. And what we see is that there must be at least 3 times Q anyons. So I'm not working this all out for you, but hopefully this is enough that if you want to, you can look at the printers. So recall Yinghai Wu was thinking about 3/4 filling. So if Q is equal to 4, this tells us there's at least 12 anyons. So we already can say the Yinghai Wu, you found the smallest number of anyons given your Hall conductivity. Furthermore, we can also down the quantum dimension by looking at the quantum dimension of this collection of anyons. Okay, so we've kind of lower bounded the quantum dimension and number of anyons. And if we look at a generalization, sorry, it shouldn't say Moore Reed, it should say generalization of Moore Reed, because Moore Reed itself will have 6 anyons, because it's at q equals 2, 1/2 or 5/2. But this is the generalization for higher fractions, has 3q anyons. So we've smashed our lower bound into our upper bound. We know that our smallest number of anyons is exactly 3 times q. And that will be true for quantum dimension. Okay, now we're going to use the condensation that I talked about before. So we now have v to the q, which I told you is this odd charge boson, and we'll violate spin c and condense it. And it will produce this theory, which is just the powers of the Wison. But this theory will have a remnant Z2 symmetry. So this, yeah, I'm debating how much I should mention one form symmetries, but the fact is that when I condense this order 2 boson, I leave a Z2 symmetry here. And to figure out the parent theories, I can gauge that symmetry. And then I rely on classification results of fermionic SPT. So I can just, by going backwards, I can find exactly the smallest theories by anyon. There are 4 of them. They're all non-abelian, and let's specialize to q equals 2. They would look like Moore Reed bar, T-Pfaffian bar. So it's all the theories that people are familiar with at even denominator. Yeah.
So the Z2 symmetry, does it permute the anyons or not?
So the Z2 symmetry is such that no, I don't believe it permeates it. Yeah, you kind of know that when you yeah. So what's the right way? You know that there's one possible parent theory. So let's say I specialize to q equals 2. U1 level 8 is an acceptable thing with sigma h 1/2. So that's one parent theory, and all the others are connected by stacking something, which would become an SPT when you condensed an order 2 boson. And that's exactly this minimal modular extension. I think, I don't know if that's clear, but hopefully that's the, yeah. Okay, so if we return to the numerical study, we were able to tell them that they found the smallest possible ground state degeneracy, smallest number of anyons, and we were able to tell them what the 4 possibilities are. So they can use chiral central charge or some other measurement discriminate. Okay, so I'll return to this observation. After doing this, we looked at the minimal states. So for odd q, they're exactly the Laughlin Jane type states, which are, there's only one example, and it's all the powers of the Wison. And for even q, there are these 4 non-abelian theories. And essentially all of these states that are observed have the smallest number of anyons. The one exception is the Reed-Rezai state, which there's some evidence to suggest that this is realized. And there's this extra Fibonacci that you can ask, like, who orders this? Okay, so now with our motivation, let's go back to the fractional quantum anomalous Hall. So again, we kind of see things that look like fractional quantum Hall, that the most prominent examples of fractional sigma h are the Jane sequence. That might tell us that the physics is similar enough to fractional quantum Hall to guess that these are also Jane-like states. Although in principle, they could be stacked with some neutral theory. So, but I think it's a reasonable assumption using Occam's razor that you get the smallest number of anyons given a fractional sigma h. We haven't done any systematic investigation of why this is in the fractional quantum Hall effect. It kind of fell out of proving what these theories are, but it might be interesting to investigate further. You could also ask what the minimal order is for other symmetry groups with fractional response. So with Meng and Senthil, we thought about the case where you have translation, U1 and time reversal. So this might be appropriate if you thought about like dimer models. This is appropriate symmetry, and you have an LSM theorem, which tells you if you're at fractional filling, you need topological order. So you can use some of the same proof devices to find minimal anyons, or a consistency machine type thing, where you start with a fractional response, some symmetry, and you work back to the consistent theories. So you could also ask if fewer anyons is preferred here, and if so, why? Okay, so with that, I'd like to summarize with a little limerick. 2 pi flux birds of Izon piercing the torus it lies on. Its breeding in a loop generates a group restricting the theory it relies on. So this is kind of a part of the tool. And with that, I'll thank my collaborators who were excellent, and I really learned a lot.
Good work, we'll leave it.
Okay. Yes. Yeah.
I was just curious about this idea that like minimal number of anyons is like guiding principle. So for like the fractional quantum spin Hall states relevant,
Yeah.
I think the numerics suggest like a non-minimal version, and there it seems like to get a minimal version, you have to do more complicated things like condensed composites and things.
That's great. Okay. By the way, I liked your paper on this. I thought it was good. So yeah, if you have a bilayer system, so say I have a bilayer system, which is like 1/2, 1/2. If they're well separated, you might expect each realizes the minimal separately. So maybe I have more read, and if I'm time reversal, I might have more read bar, or one of these other 4. As I bring them together, this is based on nothing other than Occam's razor. You might expect that they make the minimal order for the whole system rather than the 2 things separately. So in the case of like Chao Ming and Chunka had this paper that I think you worked off of. You can condense some anyon in more read bar to get to the Z4.
Yeah, I mean that's a much older story than their
Yeah.
paper, but sure, yeah.
Yes, sorry.
That's fine, yeah.
This is
But
great.
in that case, that doesn't seem to be what comes out of numerics, even when you have a.
Even when they're very close. Yeah, so I think in bio also Mesa has some work thinking about the 1/3 or 7/3 states where you might stabilize non-minimal things in bilayer systems. But it's definitely a question of energetics. So which topological order is lower, and it won't be universal. Maybe you could make some heuristic argument, but yeah, bilayer might be a good place to find Yeah.
Question.
Sorry, for the Q equals 2, you had 4, so you had Fathian, Antipathian, T-Fathian, and what was the 4th one?
Fathian, anti-Fathian, more read bar.
For Q equals 2, like 1/2, isn't more read the Fathian state?
Yeah, sorry, more Fathian, anti-Fathian, T-Fathian, anti-T-Fathian.
Isn't T-Fathian having a whole
Okay,
sector?
here, let me put up the equation. So I don't. So here we have the spin N theory where so basically the anyons here will be, if I can manage, will be like 1b squared b cubed, and there will be a sigma and a v times sigma. And the braiding rules will be that sigma times sigma, or the fusion rules, sorry, is equal to b cubed times c. And the only thing that changes is the topological spin of sigma. So this is equal to, I believe, and let me get the right. So n.
Simple charge.
This is related to the chiral, but I mean the topological spin of this sigma.
Oh, but that's like, okay, we can discuss later then.
Yeah.
I'll bother him during class week.
Okay.
Okay. Good enough. All right, thanks, Seth.
Yeah.
coming to be late, so let's come back at 11:20. Obviously.
Yeah.
Interesting to think.
Well, this is the red that is double.
Yeah.
To the-
Yeah.
to the-
Yeah. So you could, your albums get really.
Yeah, it's not that. It's not that.
And to be honest, Chicago had like a professional photographer come in. and take
Or like a
pictures of
spiral.
labs,
With a
so
good version, it's
yeah,
it's harder
like
to get rid of
They
stuff.
they were
Yeah.
good.
Exactly. So, but ultimately, I think maybe it's what mysterious. So I have to make.
I do like transit. Yeah.
Yeah, whenever I take it on my iPhone, it's like, oh, bitch. Yeah. Yeah, exercising.
Right. Alex Thomson, lucidez, opinions, superconductivity.
It's on. Upsetting. Too many people. Okay, thank you very much for inviting me to this lovely conference. See if this works. Right, so I'm Alex. I'm going to be talking about superconducting with anions. And so, not working. Okay, and so yes, not surprisingly, the subject is going to be these, discovery of the fractional quantum anomalous Hall effect that we've been hearing so much about these last couple of days. Instead of having a magnetic field and a magnetic field Landau levels, if you have a very flat Chern band, you can spontaneously break time reversal and sort of get these this fractionalization analogous to what you would see in the usual fractional quantum Hall effect. So, first seen in molybdenum ditelluride, as well as in later in rhombohedral graphene. And I keep saying this looks like a nuts. Okay, I want to talk about superconductivity. So, last year this was seen by a Longju's group in rhombohedral with 4 and 5 layers. They see they see around 3 superconducting different regions. These are sort of largely in the same area as the samples where they see the fractionalized phases. Of course, these samples don't have the moire, but otherwise, this is sort of seen as a very big step forward towards realizing both fractionalization and these fractional phases and superconductivity in the same phase. This was then perhaps actually done just last month by Tingshin in Shanghai. So they've sort of reported that they saw superconductivity in twisted molybdenum ditelluride. So this is their plot of displacement field versus filling. So this sort of region here, they're saying could be a superconductor. These are line cuts of rho x and rho xy. And what you kind of see is that, it's pretty close to this 2/3 fractional quantum Hall state. So, is it possible that you have superconductivity here emerging, perhaps directly out of the 2/3 state. And of course, we just heard about an entirely sort of different platform where these types of things could be realized as well. So it's very exciting. Okay, so so that is the primary inspiration for my talk, I guess. Really want to be looking at, how could you get a superconductor? The main motivation is sort of theories in which you can get a superconductor out of these fractional quantum anomalous Hall states. So, in a fractional quantum Hall state, you don't normally think about this because when you start doping away, from your exact filling factor, you have a plateau. The charge is immediately localized, and you're not going to get a superconductor. For a fractional quantum anomalous Hall, we now have a dispersion. So, with clean enough systems, you could perhaps avoid localizing, resulting in some sort of anion gas from which a superconductivity could emerge. So this would be in a way that is completely distinct from what you normally see with electrons pairing to form Cooper pairing. Okay, so this sort of idea here is very similar to some older ideas from the 80s. Actually, largely formulated in regards to cuprates that have sort of been being reevaluated in this new context. And so I'm not going to describe those theories. That's actually next talk, I believe. Senthil will talk about that. I really want to talk about if you have such an anion superconductor, how could you tell? So my outline is I'm going to first go over some of the very broad definition of these anion superconductors. Very loosely sketch out the early proposals. And then I'll move on to the implications. In particular, I want to look at flux threading constraints, and essentially going to show that topological order and superconductivity are an emergent intertwinement by magnetism, or by the. I'll talk about some experimental degrees of freedom, and then propose a sort of exotic insulating state that the type of physics I'm discussing could imply possibly. So this is work done with a series of collaborators, Raman and Xiaochuan at University of Chicago, Adarsh at UBC, and then some other guy, I guess. So, and there are versions of this talk where it says 2504, but it will be 2505. It will be out very soon. Okay, so it's in the 80s. We want to describe what is an anion superconductor. So, cuprate's just been discovered. What are weird things that you could do to get a superconductor? So, write down a generic matter Hamiltonian for some fermion psi with gauge field alpha, emergent gauge field alpha, electromagnetism A, with this Chern-Simons coupling alpha d alpha. So gauge invariance requires that Q be an integer, of course. And what this Chern-Simons term is doing is it's enforcing anionic statistics for these fermions. So they braid with this phase here, as opposed to regular braiding. The next step is to assume a mean field ansatz, specifically one in which you have constant flux. So the equations of motion for alpha t essentially imply that the flux has to be equal, or the density is equal to q, proportional to q times the flux, which tells us that we're at a filling factor of minus q for these fermions. So they essentially fill up q Landau levels. So the next thing you want to do in mean field theory is integrate out those fermions. Now, the fact that you're integrating out these fermions in these Landau levels, well, that gives you this minus Chern-Simons term now with alpha plus big A, because that's what the fermions are coupled to. And of course, expanding, you find that this alpha d alpha term has canceled. So that statistical term is no longer there. What does that actually mean? So really, I have this gauge field alpha here that is only coupling to one thing. There's really nothing stopping it from fluctuating wildly. And we can kind of understand of it as acting as a Lagrange multiplier. Essentially, Lagrange multiplier telling us that we can't have any fluctuations of big A. So this is a superconductor. But we could be a little bit more precise because alpha is a gauge field. It's actually an angle from 0 to 2 pi. So what we're really saying is that Q times sort of the integral of the flux has to be 2 pi times an integer. Or that the flux is quantized in units of phi q. So that's 2 pi over q, or we want to use units to be hc over qe. And so this isn't just a superconductor, it's a charged q superconductor. Still might, alpha is a Lagrange multiplier, but does it have a physical meaning? Well, yes, it can be understood as the Goldstone mode that you get from the phase fluctuations. So if this is your order parameter, you have some phase fluctuations, and alpha is sort of dual to that, to those phase fluctuations. So this would be the Goldstone mode. Of course, it's a superconductor, it gets eaten, but that is its physical meaning. All right. There are some problems, though, with this theory. Most notably, all of these local operators are bosons. That's not how cuprates, for instance, work. And the smallest possible charge is Q. So, and then on top of that, everything I just said was based on a mean field theory that the sort of validity of which is maybe a subtle question, but okay. But so let's go now back to today, where we have something that looks like it could be, we have anions, we know, and we have a superconductor, and they're not that far apart in the phase diagram. So as you're going to hear, some modern prescriptions do deal with these issues, and they come up with theories that look similar, but are not pathological. I hope I'm not upset at saying. Hopefully, I won't be contradicted in like 20 minutes. But, so this is actually out of Darius and Senthil's paper. If I just flip the diagram, you sort of dope your fractional quantum anomalous Hall state into some topological, some superconductor. So if you ignore this big red band, maybe that's what's happening here. Okay. But for my purpose, I'm just going to assume this theory. So this is a generalization of what I had written up there. So I still have this superconducting Lagrangian. I've added a Maxwell term just because we want something to restrict those fluctuations. But I also now have a topological Lagrangian. So this is something that's describing a non-trivial abelian topological order. Of course, all of these values, KMN is sort of defining the braiding of the anions, and TM here is giving you the charge. These all have to be integers again for gauge invariance. I'm also going to assume that this is a pretty clean system. Makes sense. I don't want things to localize, although it's not strict. You could have some long wavelength impurities could be present. And so based on this, I'm sort of saying that these things exist within a single system. That's sort of the primary motivation. You sort of have these two separate sectors
topological sector and a superconducting sector. My topological sector, I'm going to frequently just assume it's a Laughlin 1/3 state for convenience. So that's what's drawn here. But obviously it actually looks, just like I've pasted these two things right on top of one another physically. And for some of what I'm going to say, this is actually, this will actually hold. If you could do something and just pasting them on top, some of what, will actually follow through. And this can be kind of a useful way to think about it. And so, they decouple, at least in this theory. And so does this mean that this sort of anion superconductor, lacks any sort of unique signatures? And I think there's sort of an inverse to Betteridge's law. The answer to this type of question in a talk is always yes. So yes, let's explain why. So the trick is going to be the fact that both these anions and the superconductor obviously have to couple to electromagnetism. So if we thread a flux, we're going to see some. It's going to give us a constraint. So let's first go one by one, and then we'll put them together. So see what happens with just the superconductor flux threading, and then see what happens with just the topological order, and then we'll put those two things together. So I already just went over this. For a charged superconductor, our flux is quantized in units 2 pi over q. Typically, q is equal to 2. Now, I have had, if you actually sort of put a hole in your system and start threading sort of arbitrary flux through that, you can do that, but your system's not going to be happy and it'll have a huge energy cost. So when we want to talk about fluctuating excitations, these are the vortices that are the correct sort of units to be discussing. Get rid of it. Okay. Topological sector now. So here we can just go back to that Laughlin argument. So we know that when we thread a flux of 2 pi through the system, what that's going to do is essentially trap Tm defects of anion M. So for the Laughlin state, we know that we slowly do this adiabatic flux threading through the center of the sample. From infinity, a charge E over 3 comes in to the center, so that it's now localized on top of that vortex. And so these things, so what that's telling us is that any flux we thread through the system has to trap an integer number of these anions. So this thing here needs to be an integer. And so this and so both of these two things are going to essentially happen at once. We're going to be we add a magnetic field is going to be nucleating these vortices from the going to be nucleating vortices from the superconductor, and it's also going to be and those vortices are going to be intertwined with the anions. Okay, and so the question is then how many of these superconducting flux quanta are required to ensure that we have a integer number of anion defects. So essentially you need all of the TMs need to be divisible by Q. So instead of having 2 pi over big Q, you have 2 pi over Gothic Q, where that's the greatest common divisor. So if TM, typically TM is going to be, there's going to be at least one of these things that's 1. So that's as it is for the Laughlin state. And so if I were to thread, sort of your usual flux quantum for a superconductor HC over 2e, a pi flux, then you would trap half of an anion. You can't do that. So all of your fluxes need to double up in the system so that you are only trapping, a single anion. And generically, this is sort of what you see, at least in the models that have been built so far. This is always going to be the case, that you get this doubling of these fluxes. Now, I am saying everything I am assuming that these are anyons. The topological order is actually not strictly necessary. This argument would follow through if you have an integer quantum Hall state. The integer quantum Hall, you instead of trapping an anion, you trap an electron. You can't trap half an electron in an integer quantum Hall state either. So even in the cases where you don't get full topological order, these arguments still work. I will, however, continue to call this an anion superconductor. Yes.
So are you assuming that there's two separate Q1 symmetries? Right?
No.
So the topological sector, the charge is not conserved, right?
Yeah, but it's not conserved in units of it's not conserved in units of Q. So I would need 6 of these things to come together.
Just wondering whether the Laughlin argument works once you go through the global symmetry.
I think this is perhaps maybe an issue for this case. But I think for you could perhaps have energetically some sort of unnatural scenario, but the term that that couples them, I guess, in this case is pretty irrelevant, in that it is something where you would, in order sort of get around this, you would have to have 6 of these things close together so that this E/3 can go into the condensate, which is charge Q. Because E/3 can't go into the condensate, even though it's not conserved. If I only have one of them, the condensate is charge Q or charge 2. Yes.
I mean, even if your vortex sort of could, like, I think that there's maybe, if you said the layers, maybe I can tunnel electrons between the layers, because I think, the 2 separate U1s is like can charge. So you're saying, well, I could hop a Cooper pair from the top to the bottom, but even if you could hop a charge E from the top to the bottom, I think you would still have some residual.
Yeah, you would still be able to resolve it.
Yeah.
That's that. So
Yeah.
and maybe it's reasonable to say that, E/3 is not going to tunnel.
I think E/3 is definitely, that's fair. I think, especially especially in the.
I think if you have a chiral P-wave superconductor, you might have to worry that you have fermion zero modes and that maybe E can't tunnel.
Yes. Yeah. So exactly. Okay. But I'll keep talking about anions. So I think I'm safe. Okay. So this is something that is measurable. I've changed the flux quantization in the superconductor. So you could the periodicity of your system under flux threading is should be something you can see. So for instance, a little Parkes experiment. If you track the resistance as a function of some flux threaded to the center, it should have periodicity of phi star. That was what I called this thing is phi star, as opposed to phi sub q. Okay, but this should be true for essentially anything that we have. Any sort of quantity you measure should have the same periodicity. So here's just a generic plot from Wikipedia showing these oscillations in R as a function of the magnetic field. And here's something perhaps a little bit more relevant, where they're looking at these oscillations in twisted bilayer graphene, looking at some voltage distance across voltage distance across some interferometer device that they have. So they were able to measure the flux quantization in this system. Not very different than the things we're talking about right now. Okay, so What's my time at?
You've got 15 minutes.
Oh, okay, I have ton of time. So yeah, if you have any questions about this part, I want to now talk about the sort of thermal hull crystal state, just a slightly different. Moving on.
Are there separable symmetric and anti-symmetric parts to this?
Here, I mean, it's just the oscillations that we care about here. It's what frequencies are represented.
Whether they're like odd or even. Is that discussed at all in this paper? It's just
Yeah, I don't think that's really important for this question right now. Okay.
So just to fix what you're saying, and so take the 2/3 state, what is Q?
2. I mean, right. I'm not saying, I'm being very general. I think you need to have Q be even. And I'm kind of assuming it is 2, because that seems most likely. But it's not, 100%.
So by Q, you mean capital
Yeah,
Q
which
or,
Q?
or fractor Q?
Oh, wait, what little q do you mean?
Yeah.
Little Gothic Q? Oh, Gothic Q would be 1, I think, typically.
Which one is Gothic Q?
There's
There's the Gothic Q.
sometimes we call it the fascist Q.
If you do look up fascist font, this is the first font that comes up. Okay?
We can call it MAGA Q now.
No, in experimental units, is it H/E or H/2E? Or...
This is HC over E. Yes, sorry, I try to be a little bit careful. Everything is being quantized in units E.
Right, and so your 5 star is what? Is it
HC over E. H over E.
Is H/E.
Yes. As opposed to H over 2E. It's been doubled.
Yeah, so that is the statement.
Yeah, that is the statement, that it'll be doubled. Because yeah, so this is sort of would have half of the anion, and that's makes it unhappy. Okay, so what is the fate if we just apply sort of an out of plane magnetic field? Well, expectation is that at small enough magnetic fields, this is going to nucleate a vortex lattice that also hosts these sort of anion excitations. So now we have these excitations with sort of some non-trivial braiding in addition to the vortices. We can describe this through a Landau-Ginzburg theory. So we have here we just have that topological part that I wrote down previously, but now I've added some matter content to describe these composite objects to give them dynamics that's controlled by the field phi sub v. We can check that this theory makes sense. So if we look at the equations of motion for little alpha, for alpha here, that's just telling me that the density of these vortices is set by the magnetic field. So that's what we want. We want to apply magnetic field, and as I say, it's essentially nucleating the vortices. It's quote unquote a chemical potential for the vortex, for the vortices. And then if we look at the equations of motions for these A's, well, this thing goes away here, essentially telling us that the anion current M associated, so that's what this object is 0. So it costs energy to unbind these anions from the vortices, and so fluctuations are suppressed. Now, I'm going to be assuming that's the case. It's there are some interesting scenarios you can imagine where this is not actually a proper state. The anions do actually want to fluctuate, but that's maybe future work. Okay, so let's look at what happens when we keep increasing the magnetic field. Well, our normal scenario, the Cooper pair breaks up. We sort of get something without a superconductor. So we get metal or quantum Hall state. That's not the case. I'm interested in here. Want the phase coherence to be maintained, and the superconducting order to instead be destroyed by condensing the vortices. And again, this is assuming that these vortices are kind of these sort of composite objects, that this is the correct way to be talking about it. Again, interesting other scenarios. Okay, so right, so at when phi then is non-zero, what that's doing is it's Higgsing this combination. So it's essentially enforcing this condition here. And you can enforce that condition here by adding a gauge field beta. So essentially, you might not actually, in some cases, you can just integrate out beta, in which case you don't need to worry. But generically speaking, you're not just going to be able to integrate out beta. You now have to include it in your theory. But it's setting this combination to 0 modulo a certain certain finite certain quantized excitations, I guess. So right, so at phi equals 0, I have this intertwined vortex crystal that I had on the previous slide. And then phi non-zero, I have this I've Higgsed out this combination. And so what is that phase? So we're calling this phase the thermal Hall crystal, essentially because in the most likely case where this phi star here is just equal to 2 pi, so that's hc over e, we're able to just shift beta, which will get rid of the A field completely. And if there's no coupling to A, this is now an insulator. Now it has to be a crystal because we have some filling constraints. So it's going to have to break the translation symmetry. That means that this is in some way in a similar I think if you were to continue doping, this would be sort of compressible, so it's some sort of Wigner crystal, generalized Wigner crystal-like state. But unlike these cases, it has no sort of Hall response, but there is still topological order. And that is implying that it has a thermal Hall response. So you could say it's dark topological order. And I think by Yahui Senthil, this has been called a CDW star before. And so essentially, if you crank up the magnetic field, you could get into this sort of very exotic, dark topologically ordered state. And I guess I didn't mention on the slide at least, but the topological order of this thing here is actually larger than the topological order that existed prior to sort of condensing these vortices. So you've actually increased the sort of ground state degeneracy of the system by a factor of q squared. Right. So in reality, you would probably expect there to be some vortex liquid phase that ultimately crosses over into this. Obviously, those details aren't something I can talk about with any exactness. Maybe you could get something direct with disorder, and of course, these will be separated by first order transition. Okay, so I think I'm out of time. So the main message is that the requirement that your flux trap an integer number of anions typically is going to increase the flux quantum of your superconductor to hc over e, which could be probed experimentally. And this is something that will be on the archive very soon. Okay, there will not be a 6 there. Okay. So what to do? So one thing is it kind of alluded to the fact that I'm making these assumptions about the absence of independent anion fluctuations in that vortex crystal. And so, what happens when they're more relevant? Does this sort of imply some sort of anion Hubbard model? You can also ask, there's a ton of questions you can ask about these more microscopically motivated mechanisms for superconductivity. Are there interesting phase transitions? What other probes you can have of these systems? There's sort of a lot you can think about, especially with Sanfeng's work. Yeah, it's a lot. It's very exciting. Thank you.
Break with H or
Mhm.
to normal vortices. What should I pay?
I think you would pay a linear. It would be a linear cost. Because essentially, okay, this would be my argument. When you do that, your the topological order state is quite unhappy, sort of in between them. And so, the area, and that scales as the area, and the area where it's unhappy increases as you decrease that distance linearly. So I think it would be a linear energy cost.
Great, so these sites are not don't want to be topological anymore.
Well, I think, you're kind of breaking the topological order in between them is just always going to be unhappy. So if it wants to be, yes, it maybe there's some point if you pin them somewhere that could compensate, but I don't think. Yeah, that's what I think. I don't see why it wouldn't be, but if you have thoughts, I would be happy to hear. Hart says they go square root. I don't.
Yeah.
Yes.
Yeah, so in this model, sort of thinking of those two pretty distinct layers that are coupled essentially only through the magnetic flux. I'm wondering if you added some kind of interlayer like Coulomb effect or something, because I guess naively I would have thought, the fractional quantum Hall and the superconductor have quite different.
Well, no, but I'm actually, this is sort of this is a schematic. We're mostly interested in the case where they coexist in the same system.
Yeah, but okay, so the specific question is like, if you included in this model interlayer Coulomb interaction or something like that, or are you saying that's already there?
Yeah, it's like a single system. You could engineer something where you have interlayer Coulomb interactions, and yeah, you would have to think about how that works kind of carefully.
We're assuming short range interactions.
But not interlayer. Sorry.
So you're sort of saying, even though they're drawn as bilayers, you're kind of thinking of them as being the same electrons in the same layer.
Yeah. Because if you just because the superconductor in that case is sort of this anion superconductor, which there's it's not close to electrons sort of in the system. So there's a lot of things that maybe I'm talking about that it would just be like, no, I'm an electron.
Okay.
So yeah, so like I said, it's really useful to think about, and I think there's some potential for things you could see, but you have to get into maybe the sample details. Whereas here I can just be like, nah, it's kind of some BEC. There's phase. Yeah.
Yeah, I need to understand separately what you guys have done. But I'm a bit confused by the statement that HO2E vortex is not stable. No, there are very general results on superconductivity emerging in electron systems that the flux quantum has to be at least as small as HO2E. Going back to C and Young from the 1960s. So
But did they have anion?
Well, ultimately you have electrons, right? Unless you're violating the condition that you have electrons.
I I'm assuming that this is sort of, that was sort of what I was saying to Fiona, like you were assuming that you were in a anion superconductor, so it's, there's a gap to electrons. Well, there's always a gap to, electrons are kind of not the natural degrees of freedom to be discussing here. You're not creating electrons, you're creating anions.
No, so it could happen that the core energy for the HOE vortex is smaller than the core energy for the HO2E vortex, than for a pair of HO2E vortex. Right? But I think what you were saying, reply to Alex, is that the HO2E vortex has linear energy cost. That may have a problem. I think some finite energy difference is fine. If the HO2E vortex is still there as a finite energy object. But I think you're saying it's an infinite energy object.
You can break this thing.
Yeah, I don't see. I don't see how you could do it. I mean, without sort of killing, like if the system wants to be in the fractional, like wants to be described by this fractional state, how can it accommodate those two things at a time?
Right.
Because it can't accommodate this.
Yeah, again, we should talk separately, but the question is whether this fractionalization and so on survives in the superconductor. And it need not survive in the superconductor. It depends on that.
Okay, yeah, well, that is definitely an assumption.
Yeah.
Yeah.
Yeah, I should just give
them. All right, thanks, Alex. It's almost done. The last talk. Get cherry on the pine.
Oh, stealing your microphone.
Oh, that's not means a microphone.
I would bet.
Maybe a dangerous move.
And then be resolved.
I'm not the wrong guy to ask.
Yeah. Yes. Okay. All right, Senthil, MIT. You will tell what it is. Yes.
all right. Where's the pointer? Here's the pointer. Oh. Is there a pointer?
There should be a point. I mean,
There's
the
a
mistake
better
ones.
red.
You just happen to it.
Red. Red
Yeah,
dot.
yeah, all right, very good. All right, so let me thank the organizers for putting together this wonderful meeting. It's been great. And also thank them for letting me have the last word. So I'm going to continue on this theme that was that Alex started talking about. Actually, your talk took me by surprise because your title was something else. So if I'd known that you were going to talk about this topic, I would have had the audience of repeating some of the things that you already said. So the work that I'm going to talk about was done with two wonderful people. Jengyan Chi, who goes by Darius, is my graduate student, or was my graduate student at MIT till 2 weeks back. And Caroline is standing right out there as a wonderful collaborator. She made the long trip from her home institution to talk to us. So we have a couple of papers, one from last fall and one from just a few weeks back. So, so let me start with superconductivity. That thing Richard said that we all love BCS. We actually don't know how much we actually hate BCS. So the standard folklore for superconductivity comes out of BCS, of course. And it's we think about, according to this folklore, we think about superconductivity as an instability of a metal with a Fermi surface. Right? And this, of course, challenged. I guess how many of you know what UD stands for? Yeah, not you. Who else knows UD? All right. Martin, you're not allowed. Martin and Andre, not allowed. So this stands for underdoped cuprates. Today, in the normal state, there is no Fermi surface. At best, there are Fermi arcs. Who knows what's going on? BCS theory also tells us that we form pairs by pairing time reverse states. And breaking time reversal, if you turn on a magnetic field, that's bad for superconductivity. Right? This I think everybody knows, except that this is also challenged first by ferromagnetic superconductors, and there are very famous examples in the solid state literature, materials like uranium germanium 2 or uranium rhodium germanium, which are ferromagnetic at some high temperature scale, and then inside the ferromagnet they develop superconductivity. Right? But it's also challenged by this material uranium tellurium 2, where people see superconductivity, with very low TC order a Kelvin, somehow survive, disappear, and then reappear above 40 Tesla and survive up to 60 Tesla feeds. Really bizarre. I don't understand what's going on with that superconductor, but it exists, right? And you've seen that it's there in rhombohedral graphene and in time reversal broken conditions, and perhaps in MOT too as well. And the excitations, so that there are challenges, but this is the general belief, the general folklore. Right? Most of the time, these statements are true. And the excitations in a standard superconductor are Bogoliubov quasiparticles, which are superpositions of particles and holes. So they have indefinite charge. Charge is not a good quantum number. But nevertheless, they are directly visible in spectroscopic probes like photoemission or tunneling. You can detect these quasiparticles. They'll show up as sharp peaks, and that's done routinely in experiments. Now, let's also review folklore on the quantum Hall effect, the fractional quantum Hall effect. So the standard story, of course, is that you need a strong field in a two-dimensional system. And of course, the strong field breaks time reversal. And the excitations of quasiparticles with fractional charge and fractional statistics. So there's an anyons. And we know that we cannot create a single anyon in isolation. If you come from the external world and try to do photoemission or try to tunnel charges from the external world, you don't have access to anyons. You only have access to electrons or Cooper pairs or things of that sort. Right? Photoemission, a photon comes in, kicks out a charge. The charge has to escape out of the sample. It cannot be an anyon. It can only be an electron. Right? So these two phenomena on the surface, it looks like nobody with a clear mind should be talking about both these phenomena at the same time. Right? But of course, so the question is, what could possibly be the relationship between superconductivity and fractional quantum Hall? And early on, as has been mentioned already, Bob Laughlin had an idea that a mobile fluid of charged anyons may become a superconductor. And this came to be known as anyon superconductivity. And it was developed in the context of cuprate superconductors, and it was a really attractive theory of the cuprates, but it's also a completely failed theory of the cuprates. So people don't talk about this theory in the context of cuprates anymore. In fact, they stopped talking about it in 1991, just before I started grad school. But there was this paper with this wonderful title from 1988 by Bob Laughlin called The Relationship Between the Two Most Amazing Phenomena That Were Discovered in the 1980s. He claimed there was a relationship between the two. Right? And so there's the abstract of this paper, and you can read the sentence that these particles carrying a fraction of some quantum number attack one another by a powerful gauge force, which can lead to a new kind of superconductivity. Right? And so that was in the late 80s, and it was elaborated by famous people later on. And I believe the term anyon superconductivity comes from this paper. And with several other papers, which were all referenced nicely in Alex's talk. I'm too lazy to put them all out. In reading this literature, one has to be extremely careful. So it was 35 years back, and so the ideas are good. But not surprisingly, there's lots of incorrect statements also in that old literature. So in thinking about it in modern times, it's better to just start afresh, right? And be inspired by these old stories, but we have to think things through with the benefit of 35 years of maturity, right?
What will happen 35 years from now?
The AIs will be doing something. We'll all be dead. And I will be. Sorry. All right. So there's some problems with this old idea that Bob Laughlin had. In terms of application to the cuprates, it was abundant early on because people searched for time reversal braking, strong time reversal braking that they thought you'd need to have for this kind of story, and that wasn't seen, so it was discarded. Now we know that you do get anyons in the fractional quantum Hall effect, so maybe that's a good place to look for this. But the anyons carry fractional charge, and there's a big field, and a charge in a field does cyclotron motion. So the anyons move around in circles. So they're not really going anywhere. They just get stuck. So the anyons don't have any kinetic energy. There's no mobile anyons, and there's no question of forming a mobile fluid of anyons in the usual fractional quantum Hall context. So low doping of a fractional quantum Hall state in a 2D electron gas in a strong magnetic field, the anyons will get localized by a combination of disorder and Coulomb interaction. So you'll get the plateau. And by the time you leave the plateau, you're into the next quantum Hall state, you'll have a plateau transition. And that's what's seen. Of course, as everybody in this room knows, in the last 2 years, we have this fractional quantum anomalous Hall in Moiré materials. So these are lattice systems with time reversal, which is broken spontaneously to give churn bands, which are either fully or partially filled. And you get both the integer and fractional quantum Hall effect, both in MOT2 and in this rhombohedral graphene. So this we've heard enough talks on, so I'm not going to repeat. So the point is that this is a new setting for the fractional quantum Hall state. You have electrons on a lattice with as good microscopic symmetries, lattice translation symmetry, and time reversal. And given the lattice translation symmetry, there is a band structure for the electrons, which underlies the whole subject. Unlike in the strong magnetic field context, now there's a band structure you start with. For instance, plots like this for the electronic bands in MOT2. The time reversal is broken spontaneously, but the broken time reversal preserves the lattice translation symmetry. It's not like you're generating, you're breaking the translation, you're only breaking time reversal. And the expectation, at least based on numerics, is that the lattice translation is preserved in the fractional quantum anomalous Hall state, right? So there's a novel kind of correlation-driven insulator that's very different from any of the other strongly interacting electronic insulators that have been discovered experimentally before. Okay, so let's think now about the charged excitations of the fractional quantum anomalous Hall state. On general grounds, as Seth emphasized, we'll have fractional charge and fractional statistics for the excitations, and that's determined by the quantized Hall conductivity. Right? There's at least be one set of excitations. For instance, for the 2/3 state, these general arguments tell us that you'll have anyons with fractional charge 2e/3 and with statistics 2π/3. And there are other anyons which have a smaller fractional charge e/3 and statistics π/3. And it's an energetic question which anyon is cheaper in any given system, right? And in principle, if you play around with the Hamiltonian, it may even happen that the anyons are not the cheapest excitations. The cheapest excitation may very well be an electron. Right? That will require some exotic interaction, but it's not ruled out as a matter of principle. Okay, since the new ingredient is lattice translations, that's completely different from standard fractional quantum Hall. let's ask about how it works in these FQAH systems. So in the microscopic system, I have ordinary lattice translation action on electrons, right? The electrons translated from one lattice site to the other, and that's the symmetry of the system. So the low energy theory, I can still label excited states using their symmetry properties under lattice translation, right? So in the language that Seth was using, one should regard this as a symmetry enriched topological order that's enriched both by U1 and by lattice translations. So the punchline is that the anyons at long distances, they move in straight lines with a well-defined dispersion. They have well-defined crystal momentum. So they have a well-defined dispersion. And so the anyons have a kinetic energy. So not only do the anyons have fractional charge, but they have a well-defined dispersion. But in a precise sense, the anyons also have a fractional momentum, or more precisely a fractionalized Brillouin zone. And this comes about because the fact that I'm, say, at filling 2/3 means that if I want a symmetry preserving ground state, it's very hard to visualize how you get an insulating state at fractional filling, right? But if I have fractionally charged quasi-particles available to me, and in this case, I have particles with charge 2/3 that are available to me, I just place a 2/3 charged anyon in each unit cell, and then I can construct a translation preserving ground state. Now, the presence of this background charge 2/3 anyon at each site, this anyon will braid with other anyons. This means that any other anyon will effectively see a little bit of magnetic flux to each unit cell. So there's no external magnetic field, but there's this braiding phase induced by the presence of this background anyon. So translations acting on the anyons will not commute, and rather there will be a phase. There should be an I here. There should be a phase that depends on which anyon one is talking about, right? But this phase is such that if you think about it in terms of a flux, it's a rational flux to each plaquette, right? 2π/3 flux to each plaquette. So there's an enlarged unit cell, a 3/1 unit cell, in which the anyons see no flux, right? Because it's a rational flux, the band structure of the anyon will look like this Hofstadter butterfly at rational flux, right? And so then there's a well-defined band. And what you end up with, or in the case of 2/3 filling, 3 degenerate species of anyons that will move in a reduced Brillouin zone of size 1/3 the size of the original Brillouin zone, right? So the anyon kinetic energy is well defined. It's just that it's split into 3 different bands. Yeah.
And here you're just talking about the single particle states, right?
Absolutely, yeah, that's right. We'll do many body physics soon. So the FQAH, so I'm giving you a summary of the description of the fractional quantum anomalous Hall state itself as a preliminary to talking about what happens when you do. Right? So the state itself, so it's an insulator fractional filling of the lattice with the fractional quantum Hall effect. We have these anyon excitations which have fractional charge and a well-defined dispersion. And now we want to ask the question of what happens when we dope this fractional quantum anomalous Hall state. So the natural thing that so the most boring thing that can happen is that there's a strong first order transition, and you get out of any the local correlation that produced the fractional quantum Hall physics is destroyed, perhaps across this first order transition. I just get some boring metal, and then that none of this is relevant. Right? But I want to contemplate a more natural and more interesting scenario where when you dope the state, it's the excitations of this state that get doped in, right? And the excitations of the state are charged anyons. So now we have charged anyons at a non-zero density. And since anyons have a kinetic energy, they could potentially become mobile and not get localized. And then we have to study the problem of what a fluid of anyons do at low temperature, right? So this platform is perhaps the most ideal setting to realize the dream that people had in the 1980s of novel states that I like to call anyon-driven superconductivity. I think that I don't like the term anyon superconductivity. for multiple reasons. But yeah, okay. So what is interesting? Yeah.
Just, so I just want to understand, so, you start, of course, with some, band structure that's calculated by DFT, then you have this anion state. Are you making any claim about like what the dispersion of the anions?
No, no.
Okay.
What I'm going to say is universal enough
Okay.
that we're going. There'll be a band minimum. I do a quadratic approximation near the band minimum. Assume there's some effective mass, that's some unknown parameter. Let's work with this. At low density, that's all I need to do. Right. So why is this problem interesting, right? Why should we consider doping this insulator? Again, for I'll now look to the atomic physicists and say, as Jody told us why dope Mott insulators are interesting. We know that all kinds of cool things happen when we dope a Mott insulator. And so the real problem with the dope Mott insulator is that we have a small density of mobile charges that are moving in a background of mostly frozen charges, right? And we get, high TC superconductivity, we get pseudo gaps, we get non-Fermi liquids, and so on and so forth. And the entire problem of chip rate superconductivity can be thought of as a fight between Mott and Landau, right? Mott wins here and Landau wins here, and they somehow have to meet in the middle and, come to a compromise, right? So now what we have available to us is a correlated insulator with fractionally charged anion excitations. And then what happens when we dope? So if we replace Mott by Laughlin, because of the fractional quantum Hall effect, and then we dope, then we'll eventually end up with the Landau Fermi liquid. So now when Laughlin and Landau fight, who's going to win? Right? So that's the question. I gave this talk at Stanford last month, and Laughlin was in the audience, and he said, of course, Landau will win. As you'll see, Laughlin was right. And there I might be. Yeah. So the second motivation to consider this is that, again, for those of us who grew up working on quantum magnetism and spin liquids and doping it, in the modern world, doping is extremely easy. Right? All the experimentalists in the room routinely show how you gate and dope. Right? In ordinary solids, people look at you like you're crazy when you say take ruthenium chloride and dope it. You don't do it. So this is routinely done in modern materials, and you already see phase diagrams. So how should we study this problem theoretically? Right? So that's the real. So I've motivated the problem. Now let's ask how do we actually solve it? We could do numerics on microscopic models. This is a hard project, right? But it's a worthwhile project. I'm looking at you, Dan, in the hopes that I can inspire you to take up this kind of numerical project. But because it's hard, that's not what we did first. Instead, we tried to do something simple analytically and to use against Landau-Ginzburg-like effective field theory for the fractional quantum anomalous Hall state. And this, for the fractional quantum Hall state itself, there's a long history of doing effective field theory, Ginzburg-Landau type field theories. But now we want to generalize that to include the existence of lattice translation symmetry and use that to give an answer for what could happen when you dope the system. So, let me illustrate it by talking about the most prominent fractional quantum Hall state seen in these lattice systems, which is the 2/3 state. And we can ask about doping the charged 2/3 anion into this state. Now, the state itself is, has a description in terms of gauge fields with Chern-Simons actions and things of that sort. And then the anions will be modeled as matter degrees of freedom that couple to these gauge fields, and you'll get some effective low energy Lagrangian, which has some sort of general structure. And we can work with this field theory and then try to determine, in the spirit of Ginzburg-Landau, what the answer is when you dope the theories. And we'll get different answers and different theories depending on which anion we dope into any given fractional quantum Hall state. So let me just show you some results, and then I'll give you some understanding of some of the results. So for the 2/3 state, if you dope the charged 2/3 anion, the answer we find is that you get a superconductor, right? And the superconductor is chiral and topological in the sense that it has 4 counter-propagating neutral minor edge modes. But in the end, it's a BCS superconductor, right? So in that sense, Landau wins. Landau BCS wins. It's not an exotic superconductor. This superconductor could have been obtained starting from a Fermi surface and doing BCS theory, because that's not the mechanism through which we land in the superconductor. We land through some exotic route, but the final state is the same. In particular, it's a charge 2 superconductor. So at least in this case, we only find this superconductor. I'll put money saying that this has H/2 influx quantization. That's what the theory gives in this case. So this is an example where we have realization of superconductivity in a charged anion fluid, but at the end of the day, the final superconductor is a conventional superconductor. The only conventional in the sense that it's a BCS superconductor. The only mildly unconventional feature is that it's a topological superconductor in the sense of having minor edge modes, right? But that we know can be described within BCS. What's different is the microscopic origins of the superconductor. Normal state has no Fermi surface. It's strongly time reversal broken, right? So it's arising through some weird route, but that's otherwise it's not any different from the standard superconductor. Now, if instead you dope the charge 1/3 anion within this kind of approach, this Ginsburg-Landau approach, we don't get a superconductor at all. Instead, we get a Fermi liquid, right? But this Fermi liquid, the size of the Fermi surface is just determined by the deviation from 2/3 filling. So it's what you may call a small Fermi surface. And that's consistent with things like Ledinger, because what we also find is that we find that this Fermi liquid coexists with the spontaneous breakdown of translation symmetry with a period 3 charge density wave that's induced by doping, right? So the wavelength of the charge density wave doesn't change. It's locked at the commensurate value, but the amplitude onsets only because of the doping, right? And in the analysis, this descends from some intermediate scale non-Fermi liquid metal. But at the end of the day, as far as the ground state is concerned, there's just a conventional Fermi liquid. So again, Landau wins, right? Except that it's coexisting with some broken symmetry. So this is one of the many reasons why I don't like the term anion superconductor. If what I described in the previous slide is an anion superconductor, what would you call this? Would you call this an anion Fermi liquid? It doesn't make any sense. It's just a Fermi liquid, right? Okay, so let me give you some understanding of where the superconductor comes from. So let's think about this fluid of charge 2/3 anions, right? So we imagine we've doped the charge 2/3 anion. So the charge 1/3 anion is a finite gap. So at low energy, I have a fluid of charge 2/3 anions, right? Now let's ask the following question. What is the smallest charge that I can add to the system coming from the external world, right? So remember, I can't add anions from the external world. I can only add electrons, Cooper pairs, charge 3, charge 4, and so on. So a single charge 2/3 anion, I can't add because it's an anion. I can't add 2 charge 2/3 anions because that's also an anion, right? But I can add 3 charge 2/3 anions. One can check that it doesn't braid with anything. It's a local object, and it has charge 2. So this bound state of charge 3 charge 2/3 anions is a charge 2 local object. So I should call it a Cooper pair, right? It's the same particle as the Cooper pair. So I can tunnel in charge 2 Cooper pairs into the system, right? Now, single electrons cannot be added at low energy into the system because from these charge 2/3 anions, I can never make a single electron by forming bound states, right? So this means that if I try to do a tunneling experiment into this fluid, and I come with a metallic tip, I'll always see a gap, right? There's no way I can add an electron. But if I come with a superconducting tip, I'll be able to tunnel Cooper pairs inside, right? So I should really think about this rather than thinking about it as a fluid of anions. I should really think about it as a fluid of Cooper pairs, right? Which have somehow disintegrated into charge 2/3 anions at some intermediate scale, right? So then it's natural that once you have a fluid of Cooper pairs, no one will be surprised if it actually becomes a superconductor.
Why do you need superconducting tip? Can you have a normal tip and Andreev process on the boundary?
No. Let's say we're doing this above the superconducting transition temperature, but below the charge 1/3 gap. Right. So the system is not yet a superconductor. The question of what can you tunnel at low energy? Right. The only thing you can tunnel in is charge 2.
Yeah, but
Okay, but if you are below normal T, if you are doing, if they are doing the same well below TC.
If you're doing well below TC, you can have Andreev process. But if you're doing it above TC, but below the charge gap of the 1/3 anion, there's no Andreev, right? So then there's only normal tunneling, but the only normal tunneling you can have is Cooper pair tunneling. Right?
Is that assuming no pairing instabilities?
Sorry?
Is that assuming no pairing instabilities?
Yeah, there's no pairing here really. There's no electrons to begin with, right? I mean,
There is superconducting.
sorry?
There is superconducting still.
There is superconductor at low energy.
Right.
The ground state is superconducting, and it's a charge 2 superconductor. It's a paired. Viewed from the point of view of electrons, it's a paired superconductor. Right? Yeah. So this hopefully gives some intuition as to where the superconductor comes from. Well, let me say a little bit about the field theory. And Alex more or less described it, but I want to draw attention to maybe one aspect of it that may be relevant in a couple of minutes. So the effective Lagrangian that describes this Ginzburg-Landau theory has this form. There's at 2/3. There's an integer quantum Hall component that we should just remove, right? You can think of the 2/3 fractional quantum Hall state as the particle hole conjugate of the 1/3 state. So you take the integer quantum Hall state and then you dope holes, and the holes form a 1/3 Laughlin state. So let's just keep track of this integer quantum Hall components, but not really worry about it. And the remaining, the 1/3 state of holes is described by this theory. Now we are coupling in some fermions to this theory, and these fermions will, at low energies in the fractional quantum Hall state, that they will nucleate the physical anions, right? Now we can take this Lagrangian, write down the equation of motion for the time component of this gauge field B. And what that basically tells you is that each of these fermions is attached to some units of internal magnetic flux. So this is the old idea that you can think of an anion as a charge that's bound to some flux, right? And so because of this condition, each of the 3 species of these anions sees a magnetic field, but the strength of the magnetic field is tied to its density, which means that it's at some filling factor that's just fixed independently of the density. The filling factor turns out to be -1 for each of the 3 species. Then the natural state that you form is an integer quantum Hall state for each of these species of fermions, right? And the low energy theory, if you follow this idea through, you can work out the low energy theory, and it really, from this low energy theory, you'll conclude that it's a charge 2 BCS superconductor. And if you keep track of the thermal Hall conductance, which it's possible to do in this framework, you'll find that there's 4 Mariner edge modes. So we start in the undoped fractional quantum anomalous Hall state. The anions, there's 3 species of anions because of the projective action of translations, right? And near the bottom of their band, these 3 species form 3 degenerate quadratically dispersing bands. And the chemical potential is, which are above the chemical potential, right? So they are gapped objects. And now when we dope, we move the chemical potential, like in an ordinary process of doping a semiconductor, we move it to the middle of the band. But because these are anions, once they are at finite density, system self-consistently generates finite magnetic field. And so what you really get is this picture of doped anions, which also see a self-consistently generated magnetic field, such that each species is at filling 1 or -1, right? And then they form at least integer quantum Hall states, which, when you follow it through in the theory, gives you a charge 2 superconductor. Okay, so let me briefly mention some fun that we decided to have. So this was the analysis of the doped abelian states. And we are eternal optimists. So we said sooner or later, our experimental friends are going to find even denominator non-abelian states or more complex non-abelian states. So in anticipation of their big discovery, let's ask what will happen if you dope those states. Right? This is pure indulgence, but we are theorists, we want to have fun. And there's some numerical support for the Moore-Reed probe at filling 3/2 in models at least, but not in real life so far. But in models, it seems to exist. And here, the cheapest charged excitation is a non-abelian anion with charge E over 4. So we can ask the question, what happens when these are doped? Right? If this is ever seen, doping is easy, right? So dope it and let's see what you get. So then you have a fluid of a finite density of mobile non-abelian anions. How exotic can you get, right? But this, I think, maybe around the corner. I'm assuming June will, in a year, will find non-abelian quantum Hall states on the lattice, and then we'll have a lot of fun studying this problem. So it turns out that you can write down Ginzburg-Landau models for these non-abelian states. They are technically more complicated to work with, conceptually and technically more complicated to work with, but we could tame them and work out what happens in not just for Moore-Reed, but for many other non-abelian quantum Hall states. In the Moore-Reed case, when you dope, you inevitably end up with a superconductor, but there's different possible solutions, and you may end up with a trivial superconductor. You may end up with a topological superconductor, but in all cases, in the Moore-Reed context, at least, it's a charge 2 BCS superconductor, but perhaps it's a Majorana zero modes, Majorana edge modes. Okay, so I made this slide more than a month back, so I'll start with this slide. What are the experimental prospects for any of this physics, right? And so as of last month, this is what I had said, that the existing platform, the twisted MOT2 and N-layer rhombohedral graphene. And I said MOT2, it's tough, you need to control disorder, but these people have gotten really good at controlling the disorder. Maybe not, I'm sure there's a lot of room for improvement, but we saw in June's talk yesterday, they made it very, very clean. But then there's challenges with measuring transport at low T. But again, they have made tremendous progress in overcoming those challenges. But I have to say, I was a bit pessimistic last month. and then this N-layer rhombohedral graphene aligned with HBN. On the Moire distance side, Titep was talking about it. There's a zero field fractional quantum Hall, but the periodic potential, the effect of the Moire is very weak. One more minute. Yeah, thanks. So this potentially reduces the anion kinetic energy. So I'm still not very optimistic about this Moire distance side. But the Moire proximate side, Titep also mentioned this. There is a fractional quantum anomalous Hall state at fields as low as 0.2 Tesla. And there the Moire potential will be very strong. And so doping these, I thought might be the best place to look for this kind of physics. And of course, since the time I made that slide, this paper appeared, which which shows signatures of superconductivity near 2/3. I don't know, other people managed to extract better slides, better figures from the same paper. This is the best I could manage. So this is supposed to be the superconductor, this blue region right next to the 2/3 fractional quantum Hall state in the direction towards nu equals 1. And this is the line cut. This is the rho xx and rho xy. You see the rho xy quantized at 3/2, and then it plunges down and becomes very small. At the same time, that rho xx also becomes very small. Right? It's probably a superconductor, but it needs to be confirmed in other experiments. So the question is, can we declare victory? Right? Looks like there's a superconductor near the 2/3 fractional quantum Hall state. And I just talked about a theory where you can get such a superconductor. I don't think we can. I think we have to be very, very cautious. first of all, the superconductor itself needs to be reproduced in multiple devices and in multiple groups. I think that's the most basic thing. But even then, there's many other things that need to be studied. One thing one may worry about, and is this superconductor. So this the 2/3 state, and this the alleged superconductor, and you see that it's separated by a resistive peak, right? The resistance goes up to maybe half of the resistance quantum, and the rho xy comes climbing down, and so there's a very basic question about the normal state out of which the superconductor emerges. What is the carrier density in that normal state, right? Does it emerge from a normal state with a large carrier density 1 minus nu, in which case I should really think about it as doping the band insulator, or does it emerge from a normal state with carrier density 2/3 minus nu, in which case it's almost certainly doped anyways, right? And there's a bit hard to extract from the existing experimental data. Many of the data exists from the published data because there's an anomalous Hall. The normal way of extracting the carrier density is to measure the Hall number, but now there's an anomalous Hall contribution, and these two things add in parallel and not in series, and so it's a bit tricky to cleanly extract the Hall number. We looked at the data, but we couldn't say anything. But I think that's a good target for people to answer by doing more transport measurements. So, but given that we have some theoretical framework to think about this observed phenomenon, let's try to make some guesses. Let's ask what happens in the real device that Ting-Chen Lee has for the evolution out of the 2/3 fractional quantum anomalous Hall state. So if I go towards nu equals half, go in this direction, right? So then you see weird stuff initially, but eventually you see the 3/5 state, the 4/7, and so on. And that's the conventional Jane sequence, and it's very natural to think that it's described by composite fermion theory. In which case, what you're really doping is the charge 1/3 anion as you go towards nu equals half, right? So that's, I think, the first guess. The second guess is that as you go towards nu equals 1 on the other side, that the cheapest excitation for that may be available to dope is the charge 2/3 anion, right? There's no reason why the same anion is the one that has to enter on either side of particle and hole doping. So this is the story. Then one can potentially explain why you get a superconductor on one side and not on the other side. And then we can ask about the doping induced fractional quantum anomalous Hall to superconductor transition. Now this transition is, you can't sensibly describe it in real life without including disorder. And it's easy to think about what disorder will do. But since there are 3 species of anions which all live at different momenta, right? Strong disorder will introduce interspecies scattering and will prevent these anions from filling a nu equals 3 Landau level immediately, right? People who know quantum Hall know that the plateau jump only happen in units of 1 and not in units of 3. But if you only have long wavelength disorder, which doesn't mix species, and after conversations with June, I was very encouraged that maybe in the best MOT2 devices, that may be the right description, that you don't have point defects. So then it's possible to get a direct transition. And in the theory of this transition with disorder, it's very hard to not get a resistive peak near the transition with a universal resistivity of order h/e². And perhaps that's what's being seen. But it's early days, and the devices, I think real progress has to come from getting better devices and doing more experiments. But I think there's room for this kind of theory to accommodate what's being currently seen in experiments. Okay, with that, let me just stop. So the main point I want to emphasize is that these states are different from fractional quantum Hall, and that the anion excitations have a well-defined momentum under dispersion, right? So when you dope, there's a possibility of realizing itinerant anionic quantum matter. which is something that's fun to play with, right? And this gives us a new kind of route, not just to superconductivity, but to also the other states. And it's several other related theoretical works, one from Shogung and his gang of MIT students and experimentalists, I guess, mainly focusing on a continuum non-BCS route to time reversal broken superconductivity. I should say that nothing that I've said has any direct bearing on long juice tidal superconductivity. There is no Moire, and for me, the periodic potential is very important. And there's this other paper by Ashwin Vishwanath and his friends on induced superconductivity in a lattice model in a strong magnetic field with purely orbital coupling of the magnetic field, and where Zeeman coupling is just ignored. Once Zeeman coupling is included, the story will disappear. Right? So in terms of experimental realization, if there's a way to engineer a magnetic flux without Zeeman coupling, that might also realize this in your superconductivity. All right, let me.
I had a question about the phenomenology in Tingshan's experiment.
Yeah.
So you have this superconductor, and if you go to slightly higher displacement field,
Yeah.
so you go right above this superconducting oval.
Right.
There's this reentrant integer quantum anomalous Hall.
Right.
Is there any way to understand that through your and Darius's picture?
Yeah. I mean, we can make up a story.
Okay.
It's it's not a complicated story. The thought will be that whether you so this assumes that the underlying quantum Hall correlations have not changed. And say that you dope and you get an anion fluid, right? Now, as you increase the displacement field, perhaps what happens is that so this quantum Hall state should be thought of as a 1/3 quantum Hall state of holes, right? Now, away from 1/3 filling, maybe the holes don't want to form the 1/3 state, rather they want to form a crystal, right? A whole crystal, which will then give you an integer, reentrant integer quantum Hall state. And there's a real test of that, for which data doesn't exist. So in this reentrant integer quantum Hall regime, is there a nonlinear IV signal characteristic of depinning? But that data apparently has not been taken. It's not in the paper. It's not been taken yet. There's no reason why it can't be taken. So let's see.
Andrei, questions, one imaginary, one more real. So you said that
Sorry?
You take a superconducting state. Suppose that you are inside superconducting phase. And you said the system basically shows BCS-like property.
For long distance universal.
Did you ever thought about the situation when you start with a anionic mechanism of superconductivity, go into the ordered phase, and the system will be qualitatively different from BCS superconductor?
Right. So that there are examples that I didn't talk about. If you go to some of the Jane states, right? A good example is the 4-7 state. So then the natural superconductor that you get is a charge 4 superconductor. That's not BCS.
Right, but at the same time, again, there was Yoshan Wang created a number of stories about charge 4E superconductor as a preemptive state to a convection.
Right. So there's no state that you cannot, as a matter of principle, describe in terms of electrons.
This is what I was asking. So
So in some cases, we also find superconductors coexisting with topological order, not at 2/3, but in some of the other fillings, you get such states. We've thought about such states in various contexts in the past, SC star states. So that's just going along for the ride.
I'm also asking, you don't have any special excitations that will be localized and not propagate like in BCS superconductor?
Yeah, not as far as universal long distance physics is concerned. Once you start asking questions about short distances, then you know that where it came from.
Sure.
Yeah.
Okay, and very quickly, second question. You always make a connection to BCS.
No, I made. Yeah.
Is there any connection to BEC in the sense that is the superconductivity driven by bound state formation or by stiffness?
Okay, good. It's definitely driven by stiffness. First of all, there's a slick answer to the question, which is that this state is a chiral topological superconductor near 2/3. So that's 4 Majorana edge modes. So the BEC limit, you won't have that.
Sure.
Right? So that's maybe a too slick an answer. But given that the doping density is small and the phase stiffness is going to be roughly dopant density divided by effective mass. So that's small. Now the charge E electron gap, the gap to tunnel in a single electron into the state will be determined by the gap to the 1/3 charged anion, which we are assuming stays finite. So it will have a finite, so the pairing gap will be much bigger than the phase stiffness. So what will kill TC at low doping is completely phase stiffness.
So in this respect, you expect preformed pairs and all the beautiful stuff with stiffness-driven superconductivity.
Right, the preformed pair story will be true very close to the superconducting transition temperature, but really above the degeneracy temperature of the anions, you'll have a Boltzmann gas of fractionally charged particles. Right, so it's not, it knows that it came out of some exotic state. Right? Same stories as in the
Very
cryptos.
last session. Yes, please.
I have, so you dope, ions to the bulk, and then your conclusion, I understand that will be more like, BCS. How about?
For the 2/3 state, if you dope the charge 2/3 anions.
Right. How about you keep the FCIs and then you introduce superconductivity to the edge mode? Is there any difference to that case?
Is there any difference with
I
what?
Correlated has to be still BCS like, can you see difference from BCS superconducting on the edge mode, 1D edge mode?
Oh, somebody was discussing it. Even the fractional quantum Hall, people have talked about that, right? Making tidal supercurrents and things like that. So that story will not change because FCI versus fractional quantum Hall anomalous, fractional quantum Hall, that story will not change, right? So you have the same edge modes, and the same edge modes, if you manage to proximatize them with the superconductor.
So I guess my question is, you can also have a one-dimensional BCS like BCS superconductor. In
Right.
this case, quality is a little bit different from the one-dimensional BCS versus this one-dimensional fractional.
Yes, that is true, and that has been discussed already in the context of fractional quantum Hall, and that discussion will just go through without modification. But those 1D superconductors are certainly very, very different from let's say superconducting nanowire.
All right, let's make Senthil. Yeah, enjoyed it a lot. Okay.
Yeah, thank you so much. I guess, final comment,